So similar things we a long time computed with Ludmil.
So just one thing that, so the hotel is, sorry, the restaurant, actually it's the same, but the name is correct. And so this picture which I was drawing, so it's correct, but so the actual, so this is the statue for Alexander II, but the entrance is, so there is a street which is exactly in the back of the statue, and the entrance is not here, what I said, but on this side. And that's why it's floret, not a door. So
the same place.
The same place. The entrance is
Like robot is drawing. Picture of a robot with legs.
Okay, so let's start our afternoon session, and please utilize the restaurant story. And I have the great pleasure to introduce Professor Mohamed Abouzaid, speaking about compact manifolds and isolated singularities.
Thank you. It's a pleasure to be here. It's my first time in Bulgaria. Been living for a time in the Balkans. So I was given homework by Ludmil, which is to talk about something about how symplectic topology has to do with singularities, and the reason I've given this homework is because I made the mistake of telling him that there is some literature on the subject and that he should learn about it. I'm the one who has to learn about it. So I'm not going to talk about any results of mine. So everything that I will say today is there's some old ideas of Seidel, but I think he basically didn't write anything. The first person who actually had significant results in this area is Mark McLean. Then there are some results of slightly different flavor by Chen Zhao, who's at Kontsevich Academy. And then just 4 or 5 times at the end, I will say a few words about things that Evans and McKinney are doing, which is again relevant to this. Okay. So as an introduction, so I'm going to talk about isolated singularities. So the setup is that when X, which is complex algebraic variety, with an isolated singularity, zeros. Okay, min 0 is just a point, and you just call that point 0. Okay, and so I want to describe somehow some structure, topological structure that arises in this setting. So the first thing you observe, or the first thing we have is that so Milner constructed or observed that if you just embed this in Euclidean space, you just Cn and take a small ball around the origin and intersect it with the neighborhood with X itself. You realize that so the intersection of a sphere in Cn of small radius gives us a hypersurface, kind of a real hypersurface. In X, which is kind of the link of the singularity. And then the topology of this thing basically has no, that doesn't depend on the parameter that's produced. Now, it was realized fairly early on, I don't actually have a reference, that it turns out that this has what's called a contact structure. So I don't want to define what the contact structure is. What I will do instead is I will say that for the purposes of people who have seen something about symplectic manifolds, i.e. its product with R as a symplectic set. So in particular. So many of the things that you are used to from symplectic topology can be studied for these kind of odd-dimensional, so when you think of odd-dimensional analogs of symplectic manifolds. But the difficulty, of course, is that when you take this product of R, you get something non-compact. So you have to make a lot of R invariants don't behave quite as well. So I want to give a name to this, so I will call this something like S of X. And this structure doesn't depend on this epsilon that I choose. So if I have any tools of contact or symplectic topology to produce invariants of this thing, then they will give me invariants of the singularities. So the next thing you observe is that if you have X tilde is a resolution of X, then this sphere now that you can put a resolution of X, and that you're only changing X at the singular point, so you're not touching the sphere. Okay? And we obtain a compact symplectic manifold with boundary that is the boundary given by S of X. Okay? So I want to give this thing a name, so this will call this let's say. Okay? And so again, as later I will talk a little bit about what kind of contact invariants we have, and somehow we have some like this, Floer theory and has produced invariants of contact manifolds or things of this nature, but they're very, very hard to understand, very hard to deal with. But if you have something which is symplectic contact manifold with a filling, which basically means if you have symplectic manifold with a boundary, then we have kind of invariants that we're much better able to handle. Okay, so this is part 2. So if you choose a resolution, then you have this additional structure, not just a contact manifold, but a symplectic. 3.
Just contact manifold, but also?
So if the singularity itself determines a contact manifold, the resolution determines a filling. This is called a filling in our language.
I thought fillings have to be Stein.
No.
Oh.
So in the world of fillings, we think about exact
just need
fillings or Stein fillings or anything is a filling.
But you don't need an exhaustion function or anything?
You don't need an exhaustion function. It's sufficient that somehow there is, for the purposes of defining a Floer theoretic invariance, it's sufficient for there to be some good function near the boundary. Okay. So yeah. Okay. And that we had from the beginning. Okay. And then the last thing, which I would say that if X is smoothable, okay, which means, i.e., and let's just do like this, there exists a family xt, with T the disk. So I'm going to just, since I use this D for this thing, I'm going to use some different ball. Okay, so this is a small ball. You can see. If it's smoothable, then we have even more structure. Then you can put this together with the resolution, with the to get a family. And let me just, I don't have a very good name for this, but let me just call it, if the family, let's call it E tilde X over B. And my picture for it is something like this, that this is B, and this is this special point, and then there is maybe something complicated like this. This is D tilde X, and then this is maybe, D, what do I call it? xt. Okay, so again, but I have this xt, and in algebraic geometry, get something very big, but we want to focus on just what's happening just in the neighborhood of the singularity. So and then this is a d of xt, which is a subset of xt. This is kind of the points that lie near the singularity. Points lying near singularity. And essentially, this is the setting where Milner is basically responsible for this. He did it for hypersurfaces, and he did it without doing this resolution. Yeah. He did it for singularity, hypersurface singularities, where you can. So let me just write this. Do this. For hypersurface singularities, where you don't have to resolve. But in general, if you try to do this without resolving, you would get some singular total space, and I cannot deal, symplectic topology cannot deal with that, so I prefer to think that you're just going to pass to a resolution. Did this for hypersurface singularities and showed that there exists some kind of monodromy. What's monodromy? Diffeomorphism of non-zero fibers. Okay, B of X1 corresponding to going around the boundary. Okay, and he showed this in the smooth setting. So that fixes the boundary. Okay, fixes it. So X. I'll say one thing about this in a second. I was not expecting this to happen. There we go. But then this has since been improved. To a symplectic modular. Okay. So this is probably what Ludmil thinks about when he would probably call something like this Landau proof. Okay. So there is a thing here to be aware of. So I said that this d of xt, so it has some boundary. In principle, it's some boundary that's not the same as s of x. So this was s of x. Okay, the initial Milner fiber singularity. So in principle, this has some other boundary. Okay, But there is some phenomenon in symplectic topology and compact topology that basically says if you do deformations, then nothing changes, except possibly the class of the symplectic form. It cannot do the class of the symplectic form cannot change in a total space because the form of the total space is closed. So somehow Stokes' theorem tells you the class must be invariant. So a version of that for contact manifold tells you that the boundary of all these fibers is actually always the same. Okay. So that's why I wrote that D of x1 is, has some diffeomorphism which fixes the boundary, and instead of writing the boundary of, this is the boundary of D of x1. Okay. So we have a family of, somehow some kind of family of films.
I didn't understand what happened with the extra components in the central fiber.
Extra components.
I mean, if you blow up the total space, right, you can get extra components in the central fiber. So when you take that
Right. So I should be a little bit more careful. I should say this is d tilde x plus some pieces. Plus. I'm doing some kind of embedded resolution. I'm trying to say if you're in this setting, you can do some embedded resolution of singularities. Yes. Okay. So that's the general picture.
Can you elaborate on the LG model thing? Because I thought that way to add a VIHREN model is given by you locally have a polynomial ring, and then you scale one of the coordinates by a Laurent polynomial in the other variables.
So I mean, Ludmil models is like some kind of vague term that has many meanings depending on contexts. So here, what we're trying to do is, I mean, you can think of like any map from a certain perspective. You can think of any map from algebraic variety to A1 as a Landau-Gisborne model. You have some space, and you would like to have some invariant that is invariant to this pair consisting of this space and this function. Okay, but here and in this case, I don't want to assume that the filling, that the smoothing comes, lives over an entire, base that is all in A1. That's the first thing that I want to assume. And the other thing is that from this thing you can extract kind of AB side invariant, like randomly matrix factorizations, and A side invariant, like some kind of categories. Okay. And what I'm trying to say is that the A side invariants, these categories, they don't depend on so much structure. And this is basically all they depend on. They depend, there's only structure they depend on is you go and you take some ball that contains the singularity, and whatever you have drawn here is sufficient to encode it. Okay, so this is the kind of thing, and that, the thing we have. And then what you could try to do is you can now try to, apply all this machinery that's been developed. You can do it like this. Called apply means of symplectic / compact topology to this setting, to these settings. And I just want to point out there's somehow like three different things. There's one thing which is just contact manifold by itself, and another thing which is a contact manifold with a filling, and the third thing which is some kind of family. Okay, so let me just talk to them one by one. So the first thing you could do is you could, in the first version of the story, is look at something very called contact mode. So what is this? This is a commutative differential equation algebra associated to any contact manifold. Contact manifold. Okay? So I don't, of course, this is not the kind of talk where I will give a formal definition of such a thing, but what I will say is that if you look at, so the idea is like this. So the model contact manifold you should have in mind is S2n plus 1 sitting inside Cn. Okay. And on this S2n plus 1, if I take a point in here, well, every point spans a complex line. Line, B, C, okay? Which is in CN. And the intersection of this complex line with S2n plus 1 is a circle. So this circle is the prototype of what we call a red orbit. So there is some kind of dynamical system that lives on contact manifold. If you take a contact manifold and take a point, there is actually always a preferred direction to move, and you can just move along that flow. Now, in general, it's not as nice as this thing as the case of standard sphere, because if you take a point and you go along the flow, you're not going to come back to yourself. Okay? So in general, we expect a discrete set of orbits in a contact manifold Y. Okay? And then to build this commutative DGA, what you do is you just take free commutative algebra, generates it by these orbits. Okay. That has almost no content. Now you need to produce the differential. And this is where the pictures you will see are like this. Counting holomorphic curves in on S today, we call it S. Oh, it should be S. The contact manifold is called S today. Oh no, I call it Y. Okay, I'm going to stay with Y for now. And Y cross Y. And these holomorphic curves, I mean, you know what the holomorphic curves are. They're just like actual rational curves with some punctures going to the target. And the way that you interpret this is maybe this is like plus infinity, and this is minus infinity, and this is gamma 1, and this is gamma 2, and this is, let's say, sigma 1, sigma 2, sigma 3, and this is some expression that tells you like the d of gamma 1 tends to gamma 2 has a bunch of terms, but in particular it has plus sigma 1, okay? This number of these things tells you that there's a non-trivial contribution. Okay, so let me just try to give some idea for what this might look like in a situation which is not completely unfamiliar. Okay, so let's go back to this. Let's go back to our singularity. To singularity. And let's let y be again this x of x. So I cannot tell you an algebraic recipe for this thing, okay? Even though it's about holomorphic objects, and this is a holomorphic object, I cannot tell you an algebraic recipe. And the reason that I cannot tell you an algebraic recipe is because in general, X is very complicated and has lots of global structure. And this construction that we're doing is supposed to be something very local. It takes place just near this, there could be some complicated stuff going on. It's supposed to be took place just near this singular point, okay? But there are some special situations where you can do it. So let's say that X is like the cone on some Z. And for simplicity, I'll just make this even smooth. It doesn't, it has to be smooth. Because if it wasn't smooth, then this cone would not have isolated singularity. Okay. In that case, you just have this kind of dilation action. And there's no difference between saying I look at things near the singularity and I look at everything. It's like you can just rescale. So then we are literally counting rational curves in cone minus the cone point. Okay. So the stuff that people that do contact topology study when they study contact homology, when we specialize it to this situation, is looking at maps from P1 minus a finite collection of points. I mean, which of course you could just do it the other way. You could just say, I'm just going to look at P1 to the target. And I assume that the map doesn't i.e. maps from P1 minus finitely many points to cone Z minus. Okay, so that's what's being counted. Yes?
Z is smooth projected?
Yes.
Just trying to understand what you mean by common.
Yes, I mean, really what I meant, what I had in mind doing it in some kind of weighted projective space. Let's just make it projective. Yes. Alternatively, I could have said this is weighted homogeneous theory.
So we're moving towards orthogonal with.
This is what I'm trying to say.
Okay.
What I'm trying to say is that if you know something, not open, I would say relative.
Okay.
I would say relative.
Okay.
Okay. So there is some relationship between the curve counts that are done to construct this invariant and the curve counts. So this looks like relative. And the challenge that people have had and have not been able, kind of people, nobody succeeded yet in doing it. Challenge. Do the same. So give such a description. For arbitrary similarities. So, before saying more words about it, I just want to say, I told you what the maps are, okay? But what I didn't tell you is, that I told you some kind of, the maps are just giving you the differential in some complicated, it's a chain complex, which is this free dimensional algebra of the red orbits. So I should therefore tell you what should the red orbits be in this case. In this case, it's very easy to see what the red orbits are, because basically you just see it by looking at this picture and thinking what kind of data is encoded by the asymptotic conditions of such a map at infinity. Okay? And if you have such a map at infinity, then these finitely many points, they will basically they will converge to some point in Z. Okay? And then there will be some kind of vanishing order, some vanishing order. So in this case, the orbits, or the red orbits, are copies of, it depends on if you say homology or cohomology. Let me just say, actually, I'm not even past cohomology. Z are copies of Z indexed by the vanishing order. Maybe tangency orders. Okay? So again, something extremely concrete. And so, of course, the challenge would be to do such a thing for arbitrary singularities, and it's pretty clear. First, the idea would be you could do it whichever way you want. You can either first try to identify what all the curves are, and then think about what their asymptotic conditions are, and that will tell you what these have to be, or vice versa. Okay? But I do want to say that it's people have tried pretty hard, and it's not obvious what to do. People have tried to say, oh, maybe we should use like arc spaces as asymptotic conditions. Well, that can't quite be correct, because arc spaces only have finitely many components, finitely many irreducible components. And here you expect that there should be infinitely many irreducible components having to do with how many times you wind around. So there's been other proposals that use like Kolar's short arcs. But again, I think there's nothing clear at the moment. Yes.
What do you mean by arbitrary singularities? They're not of the form cone of Z, is that?
Yes, that's right. Not of the form concept. I mean, this is extremely special. Yeah.
But why do you expect some like algebra geometric? I mean, here you have some algebra geometric.
I mean, clearly there has to be some algebra geometric. Sorry, I don't know what to say. What I really would like to do is to say that there should be some kind of log geometry taking place right there. That's actually what I want to say. And then that's what we're doing. But I don't know how to make it precise. Yeah.
So you have a scheme and you put a log structure on it, or what?
Yeah.
And what does the log structure do for you?
It tells you that you should count log curves going into there, as opposed to curves that are actually. You see, that's the point. This thing about this cone case, I think it's kind of confusing because it suggests to you that you should look at curves that are actually very big, but actually probably you're looking at curves that are very small. Okay, but you have to have a. I don't have a definition. I'm just saying. And in fact, to be honest, what I do want to say is that it is probable that there is some. So who are these people? So Chen, Abramovich, Chen, Rose, and Siebert. So they have some proposals for kind of doing log curves and some kind of log Gromov-Witten theory, and it might very much be relevant to this problem. I mean, partly because they were motivated by some questions. I'll come back to them. That are somehow easier versions of this. Okay, so that's the kind of invariant we have, and now I can tell you what it is possibly good for. Okay, so again, it is really hard to compute this, but sometimes you can get away. You can obtain applications.
Any of these proposals have been realized in this special case?
Are we talking about the special case of the cone? In the special case of the cone, it's probably hasn't been done in general, but I would say it's if you put in more assumptions about the z, then like maybe if you put in some kind of Fano, if you assume that z is itself Fano, I think it is probably provable by, maybe I should write something. So in this special case, this is probably, but my guess is it is provable by the methods of Ganatra-Pomerleanu. So Ganatra-Pomerleanu has some, so they have some paper which again looks to not be about this. Okay, it's about some symplectic cohomology. But my expectation would be that if one were to just look at it and think about it very seriously, if you specialize in the case where z is somehow symmetrically positive, again, Fano would probably be good enough, then one would be able to prove this. But again, no actual literature. On the other hand, if you asked Eliashberg, he would tell you this is obvious. No. But I do want to say one thing, which is, it's clear that this is what's being counted. Okay? The only question is how. So what I'm trying to say is that if you take the kind of Floer theoretic definition, in this case, you can see that the moduli spaces of curves that is being counted in the kind of whatever contact homology definition are essentially these up to some very technical question about like how the complex structure is allowed to behave near infinity. Very small technical point there. But up to that technical point, it's the same moduli spaces. And the only question is how to actually write the invariant algebra geometrically in that case. And I'm saying they did some work to do this for related invariants and Pantev homology, which I'll get to. And I suspect that what they do can be applied here. Okay, so
those names you wrote on the top.
So I haven't gotten there yet. Yes, which I may never get there. That's okay. So what I want to say is that if I don't get to the end of this talk and you're curious, like what is actual state of the art in this subject, you should look at these people's papers. How about that? Okay, so there is a, so contact homology, the contact homology algebra is very hard to compute. But it is a graded VGA. It is a graded VGA. And sometimes you can use just the grading to prove some non-trivial result. And using grading, the grading carries a lot of information. So here's a theorem, about 99, by Slavsky. Okay. And it says, so this is kind of maybe the first theorem that says that there are that there are lots and lots of contact manifolds. So I have to look at my notes because that's not my theorem. So if P and prime are integers that are equal to plus or minus 1/8, then the links of the base-form singularities, I think maybe people normally want to mean of P2 are not contact. Are not, let me just say, not isomorphic as contact. Okay, so the restriction to this plus or minus 1/8 conditions to make sure that we would get the topology. So these are actually, in this case, they're all diffeomorphic to the standard sphere. Are all diffeo to the standard sphere. Maybe I should say with this Brice-Korn singularity. Brice-Korn singularity is the singularity of the polynomial x 0 to p plus, well, in this case it would be p. Okay, that's the singularity. That's the singularity for this value, for these values of p. We know that they're different standards. For other values of p, the topology can be very different. There are examples where you get exotic spheres. And what this is saying is, of course, in these cases, it's not too hard to, use algebra geometric methods to distinguish these singularities. But this says that you can see it even after passing to the world of contact topology. And the proof is actually quite simple. The proof is you basically look at the generators of this graded algebra, and you notice that they are different in different degrees. Basically, like the gap between generators between the degrees of generators is like the size of p. And so, even though you're taking a tensor algebra, which is lots and lots and lots of generators in higher degree, you just look at the first place where it has rank 2. First degree where it has rank 2, and that will be a linear function, p in order number 4p minus 2, or something like that. And then that will tell them apart. Okay.
Where is p prime in the statement?
Did I say prime? I didn't say prime. I said integers.
P and
oh, maybe they're supposed to be prime so that they're I don't want to. I think the main issue actually has to do with not being.
Okay.
I think the being on is probably, but I don't want to worry.
Okay.
Is there
Yes.
contact Caehler group that classify all this?
It's hopeless to compute it, but this basically tells you that it's really, really, really big because there's infinitely many representatives just of the standard sphere. Yes, that's how big this thing is. Okay.
Just one clarification. I don't know if you mentioned it. The contact structure you consider it as embedded into the contact structure from CM. Is it the embedded sense or is it something on its own?
Okay, so no, so when I say as contact manifold, what that means is, so the contact structure determines, it is basically given by a distribution. So let me say it like this. Usually what people do is say the following. There is a contact form, on Cn, on the sphere, you can restrict it to a contact form of this thing. Okay. But isomorphous contact manifold does not mean that the contact forms go to each other. It just means that the distribution maps to each other. So this is an intrinsic definition that is not about the embedded. Okay.
And where this 8 comes from?
This 8 comes from the, so I believe that this 8 comes from the same 8 as like signature mod 8. Okay, this 8 is there somehow to ensure that we're talking about the standard sphere. And I think if you didn't have it, then then you may end up with an exotic sphere, and I don't remember the details. Okay, so I just want to okay, so I said I would try to promise some things. So there is, so of this flavor, but much more sophisticated, so much more sophisticated recent application of these ideas is due to Zhao. So this is maybe like 22, maybe 23. I didn't write the date, I'm sorry. So he proved the following thing. So he gave some kind of, so I'll give a symplectic statement. So first I'll give the symplectic statement. The quotient of RPN, RP2n, S2n plus 1 by antipodal map does not bound an exact symplectic manifold. And this, let me just say, implies that the singularity C2n mod plus 1 is now again, this is something that I didn't check. I didn't check that you probably can just prove this by hand. I mean, prove this kind of algebra geometrically by hand. Maybe there's enough deformation to that you can just check that it's not symmetrical. But what I'm trying to say is that you can prove this by just looking at the link. That's what Zhao.
And bigger than 1.
Yes, thank you. I mean, that's also the case. Yes, both theorems. Okay. And the proof of this, I mean, what you really want, so naively what you want to say is something like, and I will say this in a second, you study the contact homology algebra, and then you observe that somehow the only solution, the only way to, if you had the filling, you'd be able to kind of solve some equation. I'll say something about that in a second. But that does not really have a solution, and that prevents the existence of fillings. But anyway, I'll say a few words. But in practice, that's not really how he does it. What he does is he kind of very carefully thinks about the contact homology of this quotient by the antipodal map and the contact homology of the sphere itself, and then does some delicate comparison to show that you cannot produce this. You cannot produce these effects. Anyway, so this is kind of where things are going, and I think somehow, if you found the right person studying contact, if you had the right singularity that you were interested in, for which algebra geometric methods were not successful, and you found the right contact topologist, you may be able to make some leeway on this. Okay.
So excuse me, this smoothable means it admits a correlation?
No, so to me, smoothable means that it comes in the family. There's a family of algebraic varieties, which goes to the singularity.
So in n equal to, it doesn't mean it's not one singularity, or it's just two?
I think it's supposed to be 2n plus 2 at the bottom, because it's 1 more than 2n plus 1.
Thank you. You have to go above dimension, above the case of curves of surfaces. Yeah. Start with 3 folds. Thank you.
One more question. This grading here is another grading than the one from the PGA?
No.
Is there a bi-grading?
No, there is no bi-grading. There's no bi-grading. This is the grading of the PGA. But the point is what I never told you what the red orbits, what degrees they live in. Okay? And they live in some degrees that have to do with, so let me just say before I put the question. So grading. So in general, this contact homology algebra is only Z1 to grading. Okay. And the grading of this contact homology algebra is something like so again it's generated by these orbits because there's some kind of flow. Okay, so you have this point, you go around the loop, you come back to yourself, you come back by transformation, and then you measure some kind of characteristics. You extract a parity from the characteristic polynomial of that transformation. Okay, so that's the odd or even. But if we are in a setting where the first term class C1 vanishes, or maybe, let me just do it like this. Then we can lift to a Z grading. And there are some choices, and the choices depend on first cohomology. So the choice is not unique. And it is parameterized by H1 of Y. Now, since we're talking about singularities, you should ask me, like, what does this mean in terms of singularities? In terms of singularities, this is the Gorenstein condition. And now it's unreadable. So if you have a Gorenstein singularity, then this contact homology algebra will have a grading. Okay. And that's what's been done here, and that's what's been done here. Okay. Now, while we're at it, there are weaker settings where you don't have a full Z grading. Maybe you have like a Z mod N grading. So you can also have Z mod N grading if N times C1 of Y is 0. To be completely honest, there's a 2 here that you can get away with. So then you can do that. And this corresponds to some kind of Q-Gorenstein condition. So this arises. I mean, of course, it makes sense. C1 has to do with the canonical or anti-canonical, whichever your conventions are. And so this tells you when you have a line bundle, this dualizing line bundle, then you get the grading in your contact invariant. And if you don't have if you need to pass to a power before you can produce it, then again, similarly, up to that power, you can produce it. Okay. So, what did I need to say next? Yes, what I meant to say is maybe explain a little bit more about what I suggested would be the naive strategy to this. So now we're on to 2, which is part 2 is when I said let's think again about smoothing/resolution. Okay, so I said there's this thing called the contact homology algebra. Okay, of Y, and again this is the contact manifold. So this has a map Q for each filling, more precisely for each exact filling. And it has a map to Q, and here I will lie and write double brackets T, okay, for each general filling. ring is somehow more precisely you'd have to complete it to get this. But I mean, this ring has some kind of infinitely many generators, so you have to be a little bit careful about what happens. Great. So now exact fillings we think of as corresponding to smoothings. And general fillings are what arises when you look at resolutions. That's how I think about it. So what do these things do? So in symplectic topology, what these do, so these maps, they count what we call holomorphic planes infinite. So remember, I said that some picture like this, maybe it should be more of them. So this, as a map inside R times Y, so this was a differential. Now what I want to do is take R times Y and think of it as living at infinity from the point of view of the filling. I'm going to call W. I'm going to use something called W. It has some topology. And then, and this is Y. And then what you are looking for are maps from, this is P1 minus infinity, so just C, literally. Maps from C to this target with some orbits. Again, remember this is red orbits. And the main thing that is proved is that if you have a filling, then the count of these objects, so now you're basically going to say, I will give it them gamma 1, gamma n, to the product of these expressions, product of the number of planes asymptotic gamma I. Then this is VGA map. Again, don't worry about it. It is what it is. Commutative function. So again, if we are in the algebra geometric setting, we should be able to interpret these planes as holomorphic curves somewhere, and we don't know how to do it in general. So, no idea, no clear picture for an algebra geometric interpretation. But if you took something which was quasi-homogeneous, one of these cone things, and you resolved it in the resolution of quasi-homogeneous singularity, this is again, you just look at the definitions and you see that you're just counting. We are counting maps A1 to this resolution of this cone, where the puncture goes to infinity, which extends to closure. I'm embedding the cone in some projective space. Okay, so it's again something familiar. So now what I want to say is that if you have a commutative algebra and you have this is like taking a point. This is like speck of you should think of this as point in the variety of this contact And that's the stalk at that point has a name. It's called linearized contact topology. Now, I'm saying this for a purpose. I'm saying this for a purpose because people who have sat through more than a handful of talks in symplectic topology or mirror symmetry or something like that have already heard some words that are related to this. Okay? So this is a symplectic by work of many people that I just want to say here. I'll just say, maybe I should say Ekholm and Luansha. Let me put all three of these. Okay, the positive action part of symplectic of S1 equivariant some other invariant, and this is invariant of symplectic manifolds. So maybe Philip talked a little bit about it earlier this week before I was here. So this is denoted, and I'm writing here, S, H, star, and there should be like an S1 here, and there's a plus. Okay, so what is this? So how does it live? So the point is that there's some other invariant called SH star S1, and I will come back to it in a second, and it has a map to this. And then there is an ordinary cohomology of the filling, okay? But I have to extend it, so I have to tensor it with the cohomology of BS1, so CP infinity. Okay? And there is some kind of example. Okay, and this, whatever it is the S1 equivariant version of some invariant called symplectic cohomology. And that maps to the functional cohomology of the Kaehler category. And in good situations, this is my surface. So what I'm trying to say is that I started by saying you have a singularity, you look at the link, you get this contact invariant. It always exists, but we don't have very good tools for studying it. But sometimes, just by looking at degrees, we can prove something non-trivial. That's this result of Slowski. Or sometimes, by being more careful, we can prove even more results. Okay? But when you choose a filling,
so it's also homology of which category?
Of the, so again, remember, I have not yet assumed that the singularity is smoothable. I've just taken a filling, which means, for example, I've taken the solution. So you can apply this. And for singularity's case, to W being something like x tilde, or maybe what I call B of x tilde for a resolution. Okay, so the only thing that I have is the Kaehler category of the filling, which is something like the category of this resolution. Okay, so now some warning. This invariant, this kind of linearized contact homology invariant, which is obtained from the full contact homology algebra by something that depends on the resolution. In fact, depends on the filling. In fact, depends on the filling very strongly. This depends very strongly in the region on the filling. E.g., if you look at A and singularities in dimension 2, A and surface singularities. So that is actually okay. Then there are two ways of filling this link. You can either pass the resolution, or you can pass the smoothing. T, which is just, you just write some other polynomial. And as long as this polynomial doesn't have double roots, this will get something smooth. Okay? So from this, and by applying, so the link of the singularity has some kind of contact homology algebra. This gives you one linearization, and this gives you another linearization. Okay? And what I'm saying is that this linearization is zero symplectic cohomology, and this has symplectic cohomology that's actually more or less the ring of functions on A and tilde is isomorphic to ring of functions. Actually, it's really more the ring of the round cohomology. So the cohomology of the heap of polymetric fields. It's not exactly correct because you have to remove something, blah, blah, blah. But to first order, approximately, it's not exactly. Don't quote this in the paper, but it's not too far from being true. It's about this size. Okay? Well, the other thing is 0. So, and both of these things are obtained from the same invariant by just picking different counts. Okay?
Can we go over this once more? So
yes. So there is this thing that I call the contact homology algebra. Okay? It is some commutative differential graded algebra. Okay? It is associated intrinsically to the contact manifold with no choices. Okay? Then you could ask, how do algebraic geometric constructions relate to it? And I'm saying, if you choose a resolution, for example, of the singularity, you will produce a map from this to Q. Okay? That's what I was drawn over here, some count of planes and holomorphic curves, that are asymptotic to the web orbits of the contact manifold, and then go inside the filling, inside the resolution. Okay? You produce this count. Once you produce this count, you can just basically linearize at this count. I mean, there's some explicit expression that's usually used in the contact literature, but it's basically like, you think of this as a ring of functions on some space, and then you look at, this gives you a point, and you look at what the ring of functions at that point looks like, localized at that point. So you can compute, I think you can compute a stalk. You can use stalk at that point, but that stalk could be 0 or non-zero, like here. Both are possibilities. Okay? And this shows that, indeed, both are possible. Now, in Philip's talk, again, I wasn't here, but I believe whatever he's doing was some kind of generalization of the fact that even though this has zero symplectic cohomology, there's still some interesting information. Okay? In fact, this is the case from which you get a filtration. You get a filtration of ordinary cohomology of A and tilde. Now, this is not very complicated. Very complicated. Anyway. Okay, I'll show you. I'll come back here. So you see, I said, I introduced this, again, there was this linearized contact homology. That's this box here. Okay? And I said this linearized contact homology, it sits in an exact triangle. Okay? And the middle step in this exact triangle is this symplectic cohomology of the whole thing. So now if this were 0, say this is 0, then these two things are isomorphic. Okay? Which means the cohomology of the filling, okay, I did the epsilon equivariantly, so the cohomology of the filling extended with some variables, cohomology to the infinity, is isomorphic to some contact invariant. And contact invariants are always filtered because they are generated by these orbits, okay? But the orbits have a length, and you can just measure what is the length of the orbit that is assigned to each cohomology class. Everything is off. This is the thing that's 0. say that this is 0, and this, we're looking at this part. Good, much better. So say this is 0. Assume that this S1 equivariant cohomology of this filling or this resolution is 0. Then what you get is that the cohomology is isomorphic to something that has to do with the contact. So this has to do with like contact manifold. This is generated by Reb orbits. Reb orbits have length, and the length of those orbits gives you a filtration of cohomology. I mean, I can tell that my arrows are going the wrong way.
How are the terms in this triangle related to CH?
Sorry, what? Repeat one more time. How is this related to contact homology?
Yeah.
This corner of it, okay, is the linearization of contact homology algebra at an augmentation. So there was a commutative algebra. Okay, the filling gives me a ring map to Q. Using that ring map, I can take stock, basically add that point, okay, and that is this. This is isomorphic to linearized contact homology. That's what I'm using. That's the relationship. So there's, again, something associated with just the contact manifolds. When you make a choice of resolution, you produce from it something else. Okay? And it so happens that sometimes if you put that together with cohomology, you get some other invariant that is related to the Fukari category. Okay? Which is how we get these vanishing. Sometimes how we get these vanishing.
So this guy is only E2, right? Symplectic.
Well,
so why is it related to something that's commutative? Contact homology is...
So, okay, so I don't know how much time I have. Minus 3 minutes. So I'll stop. I'll answer that question and stop. So, contact homology is the S1 equivariant version of a non-S1 equivariant theory that nobody has ever bothered to write down. Okay, so another way to say this is associated to every contact manifold is a framed E2 algebra, okay, which should be called the non-S1 equivariant contact homology. Okay, and this is the S1 equivariant version of it. So there's SE2 algebra starting from the very beginning. We just didn't see them because we were just focusing on some small parts of the structure. Okay, thank you very much.
Let's ask quick questions. Any further questions?
In any case, in 1 hour there will be office hours, so we can get,
You can get your fill of questions.
Let's just take Mohammed again. So we're resuming 2 minutes. Okay, so what is our selection of our selection? So, first of all, I would like to ask you please to be sure about the restaurant and tell other people that may be interested and may miss this update from the conference dinner restaurant. Is this the address? And to continue our afternoon section, it's my great pleasure to introduce you Philips Friafico, also born, where when he's going to talk about the Gauss-Mean connection in disguise, a quasi-modularic programmable invariance for the quintic.
So thanks for the introduction. Thanks to the organizers for the invitation. As you may have noticed, the title changed from what was announced. So I'm not going to talk about the T invariance. Instead, I'm going to talk about modularity for a type of modularity for Gromov-Witten invariance. So yeah, but it's yeah. So let's start. So I'll start with just a quick outline of what I'm going to talk about today. So I'm going to quickly introduce so Gromov-Witten invariance and real Gromov-Witten invariance and basically just explain like very quickly mirror symmetry for the quintic threefold. And after that, I'm gonna explain what I want to study, so which type of modularity I'm looking for. And for that, I'm gonna go back to elliptic curves and Eisenstein series. And in the end, I'm gonna relate these two words. So that's my basic idea of this talk. Basically, this modularity that I'm talking about is going to come from studying periods. But yeah, I'm going to explain what I mean by this modularity, at some point in the talk. So just so everybody understands, and I'm going to try to fix some notation. So Gromov-Witten theory for the quintic threefold. So the main example I'm gonna talk about today is the quintic threefold. So this is just quintic hypersurface. In P4, and so basically this is a Calabi-Yau threefold, and basically what we can do here is consider what Gromov-Witten theory considers this count of stable maps from a fixed Riemann surface of certain genus and n-marked points to our x, and then you can define these invariants by considering such maps with fixed homology class. So basically, we want this homology class to be a certain beta, and then we can define the Gromov-Witten invariance. I'm not going to be very precise here, but then we can define these Gromov-Witten invariants to be simply integrals or at some virtual class of this modular space of all curves of genus G marked points of a certain Gromov-Witten class, depending on beta. And so yeah, this is like very standard. I think people here have seen this. The other thing that is a little bit less standard is to consider the real Gromov-Witten invariance. Where instead of looking at like closed maps like this, we are going to consider curves with an involution inside X. Now X has a natural involution, which is just a complex conjugation. This is the natural symplectic form. I'm writing it like this because it can be considered for any symplectic variety with anti-symplectic involution. And now we consider maps like this, and then we count J-holomorphic maps as we do for the Gromov-Witten invariant. So basically what we are doing here is counting not all like complex maps, but real maps. So basically you can think of this like considering a curve with boundary, and inside your variety here you have a Lagrangian, which in this case is going to be the fixed locus of this involution. So for the quintic threefold, this is just the real points. And now we are counting curves with boundary on this Lagrangian. So this is what we are doing in real Gromov-Witten theory. This was formalized or made precise by Georgieva and Zinger in 2018, I think. But many cases were already considered before. For example, the main example that I'm going to consider here, which is genus 0, was already considered by Bacha, Pande, and Solomon 10 years before. So, but okay, so we have all these things. This is like quite well known. And one important point that I'm going to make now for genus 0 invariance. So we can define the numbers ND, which are simply the count of rational curves or the Gromov-Witten invariance for G equals 0, and the class is just this beta is just the degree. And we have this, we can consider this generating series. And an interesting fact is that, of course, these invariants are not integers, they are rational numbers. But there is this very also kind of famous formula called Espin-Wall-Morrison formula, which relates this counts this Gromov-Witten invariant for genus 0 with the actual virtual counts or instanton numbers of rational curves on X. So this for the quintic. And the thing is that these virtual counts, they are not the actual counts of curves, even when, because okay, so we don't know if we have a finite number of curves on the quintic. This is still an open problem in general, but for low degrees, we know that it is finite. But these numbers are not, they are not the actual count, because there are some singular curves on degree 5 that are not predicted by this. I mean, the singular curves are actually predicted, but when you consider double covers of them in degree 10, then you get curves that are not counted here. But so the conjecture is these are kind of the only phenomenon that is not predicted here. But that's why we call these virtual counts, and these numbers are always integers. You can do the same thing for the real invariance. And you get also these real instanton numbers. So what we want to understand is that we are looking at these Q expansions here, or here, and we want to understand if these Q expansions have some kind of modularity. So that's the problem that I want to study. So for this case of the closed quintic, this was studied by my PhD advisor, Jose Movazachi, and my work is to do a similar thing for this real case and get some type of modularity that I will explain now. For that, we have to consider the B side of this story. So let me just remind you very quickly of what happens for the quintic threefold. So we have this A side and B side, at least that's how I see things. So here we have the quintic threefold. Here we have a family Y psi of the mirror quintics. I'm gonna define this in a moment. And the Gromov-Witten invariants here, they will correspond to computations with periods of this family. And these periods are solutions to the so-called Picard-Fuchs equation that we are going to introduce. And in here, the real Gromov-Witten invariants, and this is the interesting thing, they correspond to periods with boundary on a homology class. For two curves that we're going to introduce in the B side. So, and these are solutions to a non-homogeneous version of this equation. So instead of looking at an operator equals 0, we have something here. So basically now we are going to just work on this B side. And we are going to introduce some ways to work with these periods so we can get some kind of modularity for those expansions, because we are going to see that those expansions correspond to some computations here. So let me just introduce what is the mirror quintic family, and what exactly we want to consider. So this is the mirror quintic family. So it is the resolution of singularities of this family. Let me, oh sorry, x equal to 5, x equal to 5, and x4, x4 to 5 minus 5 psi, x0 to x4 equals 0, and we consider the quotient of this by the action of roots of unity, of fifth roots of unity, and solve the singularities, and we get a family of Calabi-Yau varieties. And what is interesting here is that when we're going to consider the H3, so the algebraic Rank homology of this family, and this, as I mentioned, 4, and yeah, I mean, and it has a natural, of course, Hodge filtration, and this is going to be important for what we're going to do. And apart from that, we have this pair of curves which are given by these equations. X1, X3. And these equations, so this gives you a pair of curves here. And now what we want to consider is like a relative Lorentz cohomology. Sorry, y psi c plus c minus. And this is going to be dimension 5. And this is not going to have a Hodge structure, but it's gonna have a mixed Hodge structure. Sure. And we are going to explain what that is when, like, later in the talk. So, but this is going to be important for our work. So now, again, we want to basically use these periods to somehow get some kind of modularity for that. But to explain exactly what we want to do, I'm gonna go take a step back and consider elliptic curves and Eisenstein series. So, okay, so we are gonna, just to understand why the construction we're gonna make here is somehow analogous to modular forms or something like that. So, okay. So back to elliptic curves. Right, so I don't want to really introduce a lot of things about modular forms, but maybe I'll just say the following thing. You have Eisenstein series, which are given by the following formula. Where this sigma k minus 1 of n is simply the sum of divisors of n to the power. So it's this divisors of n to the power k minus 1, and this is also given by, if you want, this formula. So these are the Bernoulli numbers. If you want. And these Eisenstein series, they are interesting because they basically generate all the modular forms. So actually E4 and E6 generate all the modular forms for the full modular group. And so basically, and if you consider the series E2, you get the ring of so-called quasi-modular forms. Which is simply C of E2, E4, and E6. So basically we can take this as a definition of a quasi-modular form. And what we want to do here is to consider, recall that this quasi-modular forms, they satisfy a very important relation which are called Ramanujan equations. Which are the following. So if you consider the derivative of E2, you get, so I'm going to write it down. This is also kind of classical. Hopefully I'm these are the Ramanujan equations that we have for the quasi-modular forms. And that's exactly the thing that we're going to generalize. So in our work, we are also interested in modularity properties. So, I mean, for those who never seen modular forms before, these functions, E2 and E4 and E6, they satisfy a property regarding the action of SL2 on the upper half plane. But this is not so important for what we are doing. There are some results like mimicking that, but this is the property that we want to mimic. We want to find some vector field and some generating functions that will have some integrality on its coefficients. So you see that all these coefficients are integers. And this vector field here with these functions that we are going to construct are going to generate this invariance. So I'm going to explain how this shows up in a more geometric way in the elliptic curves. And then we are going to show how to do the same thing for both the open and closed case in the on the quintic. So let's do this. So we now consider. Okay, so we're now going to consider first, maybe the first definition. So we're going to consider a triple where E is an elliptic curve, alpha is a holomorphic one form, so a 1-0 form if you want. Omega is also a form but not holomorphic. Or regular, and we ask alpha omega equals 1. So basically what we are doing here, if you want, we are considering the homology of this elliptic curve, H1. We have a natural Hodge structure here, and we are taking alpha in the 1-0 part, and omega not in the 1-0, so in 0-1. Or not in the 1-0, but of course if it satisfies this, it has to be 0. Oh, sorry, it's not in 1-0. That's what I mean. So basically, this is in the first piece of the Hodge filtration, and this is in the 0 piece. So F1 and this is F0. So this is what we are doing, and we are fixing this this cup product. And the theorem. So this is also known. So we have the following thing. If we consider the moduli space of such triples, this is simply going to be given by the following. In C3, and this is the discriminant. So let me explain why we have this. So what I'm saying is that if you take a triple like this, elliptic curve and the forms, this can be parameterized by 3 coordinates in C3. And this comes from the fact that an elliptic curve can always be written in this form. So you're going to see that there is an extra T1 here. Sorry, not T3. So an elliptic curve can always be written in the Weierstrass form. And now we fix these two forms. So this is a holomorphic form. And we take omega this one, which is not the meromorphic form. And now, like this minus T1 here is just so we can consider these triples E like this, So this is E, alpha and omega, and send this to T1, T2, T3. If you wanted, you could just consider this T1 here, and then you would get forms moving, but you can consider the T1 here and you get the same parameterization. So this doesn't really matter. So this is basically how you get this moduli space. And now from this moduli space, I'm gonna try to show how you can get this vector field by considering the Gauss-Manning connection. So since we have a family of elliptic curves, like here, or we can consider T as a base of a family, we can consider the Gauss-Manning connection and on this family epsilon over T. Epsilon is just the universal family over this T, and so we're going to have this connection epsilon P to, well, maybe I don't have space. The connection to this H1 epsilon T. So this is just the RAM cohomology bundle that you get here, and the same thing here, omega 1 of T. And well, then after considering the Gauss-Manning connection, you can write it explicitly in these coordinates. So we can write the Gauss-Manning connection in terms of the coordinates T1, T2, T3, or DT1, DT2, DT3. So I'm not going to write that, but what I'm going to say is the first, like a very simple result. And then I'll try to explain why this result is important. So the result is that there is a unique vector field R on T, such that this Gauss-Manning connection is given by this matrix on that basis, and R is simply given by the following. I'm going to write it in the coordinates T1, T2, and T3. So now, after considering well, the Gauss-Manning connection, we have a unique vector field that satisfies that. I'm going to explain why we chose this matrix very soon. But the point is that this vector field is basically the same as this if you just multiply these TIs by constants, like a little change of coordinates here, and you get exactly this same vector field. And so basically, if you look at this as a differential equation and solve it by simply considering like a power series solution, you are going to get exactly this Eisenstein series. So basically what we are seeing is that this Eisenstein series is, I mean, this is very classical, but they are coming from the geometry of the family and from the Gauss-Manning connection. So this is what's happening in the elliptic curve case. I'm going to explain why this is happening. So using periods now, because that's where that's what we are going to use in the mirror quintic, because we want to relate periods which give the Gromov-Witten invariance with some kind of modularity. We want to do some similar thing there. So just so we can finish talking about the elliptic curve, so periods. So we can consider the following thing. We can consider a period map from this T to the following space, SL2Z. So it will be acting on this matrix space. So the determinant is 1, the image is positive. So this is the period space P. So basically 4x4 matrices, determinant 1, you ask this imaginary part of this product to be positive, and there's a natural action of SL2Z by simply left multiplication. And then you can define a map which takes triple and sends to a matrix like that. Where this delta 1, delta 2 are a symplectic basis of this homology, which by that I just mean that this is -1. And notice that this is well defined because whatever basis you choose here, you can always, like, it's just a change by SL2, so this map is going to be well defined. And it turns out that in this case, this map is a biholomorphism. So this is not gonna, we are gonna construct a similar thing for the quintic. The point is that we are not gonna have a biholomorphism, but we're gonna have a local biholomorphism, which is gonna be enough for getting some Q expansions. So this is the first thing. The second thing is that you can consider the upper half plane inside of P by simply considering, so I'm going to explain how we consider that. So you can consider this composition, so you can take the upper half plane, we're going to put it inside P by sending Z to Z minus 1, 1, 0. So this has determinant 1, and then we are going to use the inverse map to get us something in T, and then we can compose with these TKs, which are just the coordinates of T here. And if you do this, you just get Eisenstein series. Well, again, you have to multiply by a constant. So it's like Eisenstein series times a constant. But yeah, so basically you're getting Eisenstein series, you're getting these modular forms. So this is very nice. And the third thing and last thing, and this is the most important maybe, is that if you consider the following group G, this group G here, it acts on T by simply changing the basis of omega, because, well, if you preserve so remember that we had this condition, so it will preserve this condition, and it will also preserve the Hodge structure condition. So it acts on T, and it also acts on this period domain, and G acts on P, or maybe I should write it. It acts on the right by right multiplication. And then what you can show is that, well, first that this map will preserve the action of G. So PM preserves the G action on both sides. And also, like, if you consider consider this quotient of P by G, you get exactly this inclusion H, because, well, you have this formula in this case. Minus x4, 0, x3. So we have this formula, so basically this is like an element in H, and this is just an action of G. So we have this, and the point is that this vector field R, and then if you consider, so the Gauss-Bonnet connection restricted to this H, and when I'm writing H here, I'm just writing, considering like this subspace H here in P and looking at the pre-image. And if you do that, you're going to see that this is just 0, 1, 0, 1. So basically, and this is easy because you can just consider the Gauss-Bonnet connection using these coordinates here. So it's easy to compute. So basically what I'm saying is that this R is generating a one-dimensional subspace of this T, and this 0, 1, 0, 0 is just coming from looking at the Gauss-Bonnet connection in this natural subspace of the period domain given by the quotient by this natural group action. So this is why this choice of matrix is natural, and this is exactly what we are gonna do for the quintic threefold. So I still have, I think, 15 minutes or even 20 minutes. So yeah, so it's enough time to explain the picture on the quintic threefold and what exactly we get there. So, well, first we're going to start with the closed invariance. So this was done by Movazachi, 15. So basically it's exactly the same construction that can be done in the elliptic curve. We are going to consider a mirror quintic with a basis of the third de Rham cohomology, so the algebraic de Rham cohomology. So this is so alpha I is third de Rham cohomology. Now I'm using a coordinate z. Back there I was using a coordinate psi. If you want, you have that z is this, but well, it doesn't really matter too much. It's just a one-parameter family, and we have that these alpha i's are in the right pieces of the Hodge structure. So we have a Hodge structure here. So it's exactly what we explained. 5 minus I H3 Y Z. So these are in the right pieces of the Hodge structure, and this is fixed. This is going to be this matrix. So 1, 1. Sorry? This is going to be this matrix, so it's going to be fixed. So again, we're just considering this basis with compatible with this Hodge, with the Hodge structure. And now we consider again the moduli space of such things. So we're going to define our T in this case, and it's also going to be a affine open set, like an open set of the affine space, given by this. So, and we have this coordinates T0 to T6. And basically how you do this, you just look at this basis, and first you consider So first you have a natural holomorphic 3-0 form because this is Calabi-Yau. Then you consider the derivatives or the Gauss-Manin connection. So something like this, and the second derivative, omega, etc. So you have 4 because it's 4-dimensional, as I said. And then you can just choose a base change matrix so you can get some alphas, or alpha 1 to alpha 4, satisfying these two properties. So then you can write coordinates for this S, so you can write TIs, T0, T1, T3, etc. And then you just check that what happens if you ask these two properties, and then you're going to get relations among these TIs here, and then in the end you have 6 independent ones, and you have these relations in order to everything to be well defined. So that's what you do. And so yeah, so you ended up getting this. And now we can use the Picard-Fuchs equation to write the Gauss-Manin connection. So I'll just say what the Picard-Fuchs equation is. So it's given by this. This formula. Delta plus 3/5. Delta plus 4/5 equals 0. So this is the equation. This is the operator, let's say. And the fact that this equals 0. So basically, you can this shows that if you consider a holomorphic form, you have this equation that is satisfied by the forms, and then this allows you to write exactly the Gauss-Manin connection in this coordinate as considering simply something like that. A1, A2, A3, A4, where this A1, A3, A2, A4 are just the coefficients after you write this equation on the coordinate z, because I didn't say, but theta is just this. So after you expand everything, we're going to get an equation of this form. And well, then you can write the Gauss-Manin connection as this in the basis, like omega, that basis I first wrote, the basis of omega, the derivative of omega, etc. And then you use the change of coordinates to get this connection in this basis alpha. So this is how you write the connection in this basis. I mean, this is all very elementary.
What's eta?
It's just a differential form. And in the end, you get a similar theorem. So basically, like, the thing about this Picard-Fuchs equation is that the periods of this of the differential forms in X satisfy this equation. So that's why you can get that's why you can use this to write the Gauss-Manin connection. So basically, these objects are just two different incarnations of the same thing. And the theorem is the same thing. There is a vector field, unique, and a unique regular function on T, such that the Gauss-Manin connection applied on this vector field is given by this matrix 1, y minus 1, 0, 0, 0, 0, 0, 0, 0, 0. And okay, and many of you might recognize this from like the Yukawa coupling, Y as the Yukawa coupling, and this is the Gauss-Bonnet connection on the D model. But I'm also going to give a similar interpretation to this soon. And the nice thing is that now if you consider this vector field, and if you, so this vector field is going to be something like this, T0, T1 dot, T2 dot, until T6 dot. And if you consider these vector fields, and if you just plug power series here, Q expansions, you're gonna get that this TIs have integral Q expansions. Well, except for like the first term here in T0 because it's a fraction, but like, yeah, so, but they have basically integral Q expansions. And like the Eisenstein series, and again, you can write this Y as a function of this T0s. So basically, and we know as well that Y, simply by considering classical mirror symmetry considerations, that this is the Gauss-Bonnet connection. I'm going to explain this with the period soon, but we know that this is exactly the given by this Q expansion, where this and these are exactly the instanton numbers I mentioned earlier. So again, we are finding like a system of functions the same way as the Eisenstein series is, and we can express this Gromov-Witten invariants or instanton numbers in terms of these functions. And they have also integral expansions, and they also come naturally from the Gauss-Bonnet connection. So it's exactly the same, like a generalization of the same situation. So this is the type of modularity we get here. And now I'm just going to explain how to get this in the open case, and then I'm going to talk about why we choose this matrix. Like besides, okay, besides having like this matrix from already other places, but we can get to this matrix by the same considerations of considering the action of a group G and a period map. But before going into that, I just want to talk about the open case, or the real case, which has some differences. So now we are also going to consider the curve. So we're also going to consider this, but now we're going to consider a basis for the relative homology with boundary on those two curves. And now we don't have a Hodge structure, we have a mixed Hodge structure in this place, and this is coming from the long exact sequence. So just if we write this, this is maybe not the best place to write this. So we have this exact sequence. This is going to be 0 here because these curves, well, they are curves, so we don't have homology here. And now, basically, we are looking at this space. It has dimension 5. This has dimension 1. And basically, the 4, so we're going to have 4 elements here coming from the closed homology. So we have 4 closed cycles, let's say, and 1 open cycle coming from here. And now we can define a mixed Hodge structure. So let me just explain what I mean by a mixed Hodge structure. So we have now two filtrations, a weight filtration and a Hodge filtration. So this is increasing, this is decreasing, and so you know this by W, by F, and the thing is that F induces a Hodge structure on the quotients by W. So this is basically a mixed Hodge structure, and in our case what's happening is that, of course, we're going to have W0 equals 0, W1 is going to be the image of this map that I'll call phi, and W2 is going to be the whole thing. So I'm denoting like this, but it's the union actually. Well, and we also have W3, which is the same thing. And if you look at W1 over W2, so W1 over W0 is simply this, which has a Hodge structure given by the Hodge structure in this absolute cohomology. And W2 over W1 is simply this quotient, which is given by H3 of Y, which also has a natural Hodge structure. So I'll just write like this, have natural Hodge structures. This is actually a very specific case of a very general theorem that all these relative cohomologies have mixed Hodge structure as well as open variety. So if you want, you can look at Peters and Steinbrück. Maybe that's the best reference for learning these things. And just again, it's the same story. Now we can have a moduli space S given by coordinates like this, S8 in C9. Now you have two extra coordinates, S0, S5, S4, S4 to the 10 minus S0 to the 10, different of 0. So this is the space that we get. And basically this has a relation with the closed curve space. But okay, maybe I will not mention that. And the thing is that there is a unique vector field R and Y and F, so these are regular functions such that you have 0, 0, F, 0, 0, 0, 0, 0, 0, 0, 0, 1, Y, minus 1, 0, 0, 0. So now the Gaussian connection is given by this, and this Y is the same, Y as before, the Yukawa coupling, let's say. So this is basically counting closed curves, because of course you still have your closed cycles here, so you expect to get something regarding the closed curves. And F is this product S7 times Y. It's interesting because this S7 times Y here is actually, this S7 is actually called terminator. This is important if you want to consider higher genus things. I might mention this in the end. And this F is the count for real. Yes. 2 more minutes. Okay. Is the count of real. So count of real. So just so I can go real instantaneous. Notice that here you have this square root that appears. This is because of the way R is, so we get the square root in the end. And also because when you write, in order to get this, you need to write this Gauss-Bonnet connection in terms of the coordinates, and this comes again from looking at the Picard-Fuchs equation, and here the Picard-Fuchs equation is, as I said, non-homogeneous, and you have this term square root of z, so that's why you're getting the square roots here. So since I don't have a lot of time left, I just wanted to mention that you can again look at the period map like you did for elliptic curves, and you would get a nice map with the periods, and then you have this group action. If you look at the quotient of this group action in the period domain, you get a one-dimensional space, and this one-dimensional space is actually the space which this R is generating. So that's how you get this R. And I just want to say that a future project is to show that these functions not only generate this dimension, just genus 0 coefficient numbers, but also higher genus instanton numbers. So this is true for the closed invariant. So you can also write the higher genus generating functions in terms of these TIs for the closed case. And a project that I have is to try to do that for the open case. And this is involves like considering these anomaly equations and things like that. But well, since I'm
So what is open?
sorry, I mean real. It's just because basically we are considering this curves with boundaries on the Lagrangian. If you want, you don't need to consider the real Lagrangian here. You can consider other Lagrangians, and this is more general. So, for example, if you consider other curves here in the B set, so if you take a different Lagrangian here, you're going to get a different pair of curves here, and then you have counts which are not really, I mean, it's not clear what are the enumerative meaning of that, but this was done also by Sebastian Henning. He considered a different type of curve here, and he found a Lagrangian on the quintic which and saw how the invariants actually are related to these counts. But those invariants that we got were not integers; they were irrational. But yeah, but what I mean is that you can also consider real higher genus curves and show that all the instanton numbers for all genus are actually satisfying, like are actually written in terms of these S's, and this would be some kind of modularity result. So that's what I had to say.
Any question?
I think it's 16 pi squared.
Ah, yes. You're right. Sorry. Yeah, it's true.
Any other question, comment? Okay, so let's sing this speaker again.
So let's have a 2-minute break and then quick 25 minutes office hours with
This won't take long. I'll try not to take it. So where does that stop?
This A and A2, the
Yes, yes. Okay, so I stopped where I made this statement. Okay, fine. Maybe I'll first repeat the last statement I made and make sure. Okay. So, maybe I'll make a table. So this is like the singularity part. This is x. And then this is the kind of the symplectic part. So this singularity x gives rise to this contact manifold, which is this x. And then this is this kind of x tilde. That gives rise to this kind of call it dx tilde, which is filling of Sx. Okay. And now, then there is the kind of third type invariance. And then, so this, I'm just repeating. So this is the contact homology algebra. X, and this is this kind of ring map, algebra map from contact homology algebra. Okay, and I did say something about, I answered to Kramer's question, that somehow this is probably not the right thing. Okay? This contact homology algebra is some kind of S1 equivariant theory, and it has a non-S1 equivariant analog which hasn't been constructed. Now this
I actually missed the content of that. So the S1 equivariant is just the Reed vector.
This is loop rotation.
Right. So what will be the other typical invariant of?
Same thing. It'll be an invariant. So
how is it going to fill the contact structure if it doesn't fill?
Same thing. So what you do is this is generated by Reb orbits modulo unparametrized Reb orbits. So this is going to be the S1 equivariant theory of a theory which is built from parametrized Reb orbits. So, okay. And you can see a shadow of this, because if somebody ever asks you, this is contact homology algebra, then let's do this.
Yeah.
When you augment it, you get a stock, some kind of stock, which is called linearized contact homology, and which also happens to be this, now what I wrote, symplectic cohomology, and I put an S1 here and I put a plus here, and this is part of, so this is the corner of this exact triangle that I wrote, okay? And there is like an S1 here. And if you ask me, for example, what kind of structure this has some kind of Lie bracket, it's an L infinity algebra. But it's basically there, it's Lie because you start with something commutative, and then there's S1 action on this kind of descended the circle. Instead of having a product, you're going to end up with a Lie bracket. If you have topological space with a product, this is what you get. Okay, so and then the point that I made is that these stocks, whatever, this linearized contact homology are extremely sensitive to the resolution, to the filling. Okay, I did also want to say that it's not just the resolution that gives it the resolution. Even the smoothing also gives rise to this algebra map, and the smoothing gives rise to more. So here we give smooth. So this gives rise to a filling, another filling, plus some kind of monogram. Okay, this is what I didn't get to say. But let me just stick here for a second. At this stage, what I said is that example, and surface, okay? And in that case, if you apply it, you get 0. You get the 0 again. Now, I want to pause for a second.
If you apply SH without the plus, you get 0. That's what you're saying.
Yes.
So which is,
yes. Thank you.
Those are different.
Yes, absolutely. So get that, and then we'll say like this: S H star S1 with the plus, since this is what I'm talking about, of this D of x tilde is isomorphic to the cohomology of x tilde with this kind of tensor cohomology of CP infinity. Okay. So as a consequence of the fact that the third term in the exact triangle is 0, you get the two things are isomorphic to each other, and that's when I made the comment that this the vanishing statement may suggest to you that there's nothing interesting, but actually it tells you something interesting, because now you have a filtration of this group, ordinary cohomology. Okay? And what Philip talked about is some, I believe, I don't know what he talked about, I believe he talked about some generalizations of this phenomenon. Okay? So before going further, I put 3 names down, just because the 3 people that I feel like contributed quite a bit. So, just while I sit here, I think this dependence is probably like, the first place where there is room for even more fruitful interactions between symplectic topology and singularity theory, because it tells you some completely different way of trying to distinguish or kind of study possible different resolutions. Okay, and Mark McLean had this very interesting result. So Mark McLean, about 14, proved the following thing. He proved the result that says if a Q-Gorenstein threefold singularity has link, which is standard contact S5. Okay? So S5 lives inside C3. So basically, like, if it's the same as the link of the something which is not singular, then in fact it is smooth. Okay? And I think this is kind of the first kind of non-trivial result in the subject, which is why I had his name up there. And the point is that Mumford proved that if you have long time ago, if you have a surface singularity whose link is smooth S3, standard smooth. Well, I guess by now we know that there's all topological S3 smooth. Some didn't know it. Anyway, then there's no singularity. Then analogous result. Okay, but Mumford's result was about just the topology, the smooth topology. Okay, and Bierskorn and similar, basically showed that in higher dimensions you couldn't hope to prove a version of Mumford's result, and so this is the best we can hope for. Okay, so
why cannot prove?
because Bierskorn's theory, they tell you that there's lots of different contact structure on the smooth standard smooth tensor. But this tells you that actually, if you think about the smooth the contact structure, then you remember much more. Okay, and he proved this again morally by studying exactly this story here, this link to singularity, and kind of relating the grading on contact homology. So it's a key tool. Okay? So he relates the Q-Gorenstein setting. So as I said, that's exactly the setting that allows us to have some kind of Z grade, some kind of grading of contact homology. So key tool is to relate the degree of rev orbit. I told you there's some integer you can get even though orbit to the discrepancy of the divisors that you get when you resolve, okay, a component of resolution. Okay, and what is this discrepancy? It's basically saying, well, there is some kind of holomorphic volume form floating around. That's why we create Q-Gorenstein case. It takes tensor to get it. And so then you can pull it upstairs and look for poles. Okay? And that is some invariant. You can look at what is the minimal discrepancy, for example, and he relates these two things together. But kind of this is the kind of circle of ideas that would be explored. Okay. So maybe I'll more or less stop here. I'll just say that if you have a smoothing, then you have even more structure, as I said before. So, so the additional structure that we have is, as we said, we have this monodromy. You can go around singularity. So fiber, so smoothing xt has a simplex morphism. And there hasn't been too much done on trying to kind of develop, kind of symplectic invariance of singularities from this point of view. But I did want to point out that, as I said before, as I said in the talk, this non-S-monic covariant version of this theory is supposed to be related to the Hochschild cohomology of the Foucault category.
You didn't say which Foucault category. Is this compact Lagrangians?
Good question. So, Hochschild cohomology tends to be relatively robust to changes, but of course the answer is you should take non-compact ones. Okay? That will be the thing that's safe. Unless there is enough causal duality floating around to be able to switch to the compact ones. But I also put two names down. That's the Keeley. 21 maybe. So what they've been doing is they've been studying, study what I think of as like the total space of family of ABE singularity, surface singularity. Okay, so there's some name for this. It's compound Duval is what they're called. Compound Duval. So you just imagine you have some threefold singularity, and if you slice it, it lives over some base, usually W, and over the base, over the origin, it's just given by some ABE singularity. Okay, and then this ABE singularity maybe singular like this, and then it deforms a little bit. So you have this total space in this form. Okay, so how do they study it? Well, they study it by using kind of even more. So even some settings where not only you have a smoothing, but you actually have some kind of morphifiable. You can kind of use, but in the singular case, this is probably good enough. So use morphification of the singularity to adapt some kind of techniques of Seidel. Now you get to this Foucault Seidel category. Seidel techniques for studying Foucault categories. So what they do basically is they say, oh well, you have a singularity, it's pretty bad, but you can kind of move it away and kind of turn it into just a bunch of ordinary double points. And once you turn it into an ordinary double point, then this Foucault category you can kind of not quite algorithmically compute, but come close to it. Seidel has some kind of inductive scheme. And so they computed quite a bit.
So W here is XT or?
The what?
W here is XT?
W here is like an auxiliary parameter. So what I'm saying is that you take x0 and you assume that x0 itself is a threefold.
Yes,
with
in the symplectic homology.
Oh, so this is W is yes, here W is xt. Yes, thank you. Yes, absolutely. Yeah. So what am I trying to say? What I'm trying to say is that yes. So Seidel had some kind of machine, kind of developed a kind of inductive scheme for computing Foucault categories of left-shift vibrations, basically, which you can think of as morphified singularities. And his inductive scheme, partly relies on mirror. You can kind of combine it with mirror symmetry, which is fairly well understood in these cases, to actually start computing these groups. Okay, and they computed enough that they actually came up with like a conjecture, which I know nobody knows. I mean, like, I just want to say it because it's so they have a conjecture, which is a criterion. So they came up with a conjecture. Criterion for existence of small resolutions. following thing in terms of the rank.
This is dimension 3.
In dimension 3, yes, in dimension 3. Of course, the singularities are small. The singularities, that's not a problem. I mean, we know what they are. I mean, they can't have small resolutions because there's not enough room for these threefold singularities. So for these threefold singularities. In terms of the rank of SH being constant, symplectic, look at the symplectic homology.
So this is the symplectic small resolution?
No, I mean algebraic ones. I mean,
in particular symplectic.
Yeah, in particular, well, no, we can have, what you mean symplectic is like, no. They really mean like
Homomorphic.
Homomorphic, yes. In terms of the rank of SH, what's the rank? Rank of SH being constant for star less than 1. Okay. I mean, I just want to advertise it. Again, there's no theorem yet. The theorems are all, currently in their work, the theorems are still on the form like, we computed all these cases, look, it matches up. But it somehow, it's up, kind of given the kind of things that McKinney had proved, it looks optimistic that one would actually be able to kind of start pushing these techniques further. And the reason that I wanted to end with this, and I am going to end, is because, this is, while the statements only use this symplectic homology invariant, the actual computations really rely heavily on mirror symmetry. Because you just cannot compute these things directly. As I said at the beginning, compact homology is really, really hard to compute. Usually the only thing you compute about it is some kind of Grady conditions. But if the rank of symplectic homology is constant for degree above, for a bunch of successive degrees, then there could be lots of differentials. And they're basically saying, like, under some situation where you can ensure that the things survive all these differentials, then you obtain some obstruction to small resolutions. I mean, I don't yet have a good explanation for why it might be true, but it seems to be true experiments. I think that's what I'll say.
One more quick question. Pranav,
I was going to ask the famous question, what is an atom? Can someone write down a working definition of an atom?
Okay, but but I have 3 minutes to answer that question.
Or later.
Okay.
Are you asking what's an atom abstractly or what's an atom of a variety?
No, a variety. Oh.
Huh?
Okay, no, you have 2 minutes.
Yeah. Okay, 2 minutes. Right, so for a variety, so say X is projected, right? And smooth. Then what you want to do is, to such an X, there is so this gives you some super manifold, which is rigid analytic. So this over C, and you need to because these atoms are in order to work with them, you really need to think about them as analytic objects, and you don't know the convergence of the quantum product in the complex topology, so you have to work over a non-Archimedean field where the convergence can be forced by hand. By just gross estimates for powers. So what you do normally is embed C into some non-Archimedean field for which the valuation is trivial on C. The typical choice is you take C and then QSO series in some auxiliary variable. Form of QSO series in auxiliary variable. So if you have X, this gives you a super manifold which is analytic over this field, let me call it K. And what this thing is, it's some domain. It's a rigid analytic domain inside the supermanifold which corresponds to the homology of X with coefficients in K. Whereas, you know, you think about this as a super guy, so the output homology corresponds to just modification of the function here. Okay, and over this, you get, so this is the first thing you get, and then you also get an analytic vector bundle V, which is trivial. It has again fiber, homology, coefficients in K, tensor with the analytic functions. And this thing has a quantum connection coming from the non-Newton invariance. So this is a connection on, so let me say that this is really a bundle over B cross a formal disk with one variable U. And this is a connection on that page. I mean, the usual thing has it's given by the usual formulas, Brownian formulas, except that you have to put all the homology classes because you need them.
So this is parameterized by divisors. Yeah.
Say it again?
No,
not divisors, everything.
So
everything. No, it's definitely everything. Yes.
Is the size of the analytic domain something like the smallest power of y occurring in an invariant?
Yeah, something like that. Okay. But it's slightly trickier than this because I mean, you know, it depends on. So inside. Is related to what Victor was asking, right? This thing breaks into H2 plus H even not equal to 2 plus HO. And so this just contributes to the function theory. These guys, they give you some real actual even directions inside the manifold. And this thing inside has the ample cone. And so that in principle transcendental classes in H2 and the Shishadri constants for those transcendental classes also limit the size of the domain.
The what classes?
The Shishadri constants. So yeah, so that's the. But there is some explicit estimate that you need to do in order for everything to become convergent in this. Anyway, so you have the quantum connection, and it has a lot of. So this is what this variation of non-analytic Horst structures is, and it has a lot of residual structures. In particular, there is one part of the residual structures is so this is not data. This is just follows from everything that's written here. So there is one residual structure which is kappa, which is the coefficient. This quantum connection happens to be framed, so it's just the coefficient in front of the second order pole. in U. And this thing commutes with everything. So kappa is an endomorphism of H0. So H0 is this H restricted to B at the close point, and it's an endomorphism. And this is the quantum multiplication with this class, which is, so this looks like the canonical class and the anti-canonical class plus a class which is something like I don't know, even homology classes minus 2 times the identity over 2. So these are times the dual variables. So this delta I is even and not 2. Sorry, well, I don't need to say degree. Degree delta I minus 2 times the identity times the dual variables. So it's just the quantum multiplication with this class. This is the Euler vector field. This, this is the analytic Frobenius manifold associated to their model, and this is the Euler vector field for them. And then what you do is you take the, so this gives you an endomorphism of this bundle, and in particular gives you a spectral cover for that. You have a spectral cover for that endomorphism, so you can look at the whatever the characteristic polynomial. Inside B times the rigid affine line. So this is some cover, let's call it sigma x, sigma. And the reduced cover mapping to B is just a finite cover, parameterizing the eigenvalues of kappa. And you just take basically the irreducible components of that guy. So you take the complement of the branch locus, let's call it U, and its pre-image inside here, let's call it U twiddle. So now the cover became unramified. And an atom is just a connected component of U twiddle. Well, it's slightly more than that. So you look at the connected components. So for every connected component of the twiddle, so that's an eigenvalue of kappa. So for every alpha, which is in pi 0 of U twiddle, you have a connected component, which is U twiddle alpha, mapping to U. Over this guy, you still have H and alpha. You can pull them back. So this again is Frobenius manifold data on U twiddle. And then you take the germ of that at the top. And the generalized eigenspace, so an atom labeled by alpha for x. This is just the H alpha number alpha, which is the generalized eigenspace for alpha for the action of kappa. And you want to take the germ of that at some point. And if you want to put real, if you want to keep track of extra information, like in order to get abstractions to rationality, you want to look at this whole picture together with the action of some motivic Galois group. So, in particular, the Manford group for a smooth projective guy will act on this. Will act on this. Everything will be equivariant, and you take the germ. So you take the germ at the point which is fixed on the Manford group, which will be just a Hodgkins. And so that is enough.
Okay.
I answered.
All right. So
Yeah, sure. So we continue with this afternoon session. Thank you so much, Tony, for the explanation, and also to Mohammed. And thank you guys for being here. So now it's the talk of Hugo Catarrucci-Botos from the University of São Paulo. That's going to talk about some orbit bundles over spheres. We're gonna do
Do you keep the lights on? Is it clear to see?
Maybe some of them.
Yeah, like the back ones.
So,
yeah, that's good. Yeah.
Okay. So my talk will be about complex hyperbolic geometry. So let me more or less explain what I'm going to talk about. So consider a surface. Later we'll consider an orthofold. This surface is oriented, closed, and have other characteristics negative. So you can assume that S is hyperbolic, right? So it's the Poincare disk quotiented by a function group, right? And I want to study disk bundles over surface. By disk bundles, I mean disks, open disks, okay? So disk bundles. When you are on this situation, you have just two invariants for these objects. You have the Euler characteristic of the surface and the Euler number for the disk bundle. Okay, if with these two invariants you can determine the pair once again. Okay, you just need these two invariants. So in essence, what we have is two parameters. We have the Euler number and the Euler characteristic. Right. So how do I pass to the next one? So when you study surface, we have a relation between geometry and topology, which is you have the surface as emits hyperbolic structure even only if the characteristic is negative, right? In the same sense, you can consider the following conjecture. Consider oriented disk bundle over a closed oriented surface with negative Euler number. Then you have a relation between topology and geometry. This is a conjecture by Gromov, Watson, Thurston, from 1988, where they were trying to understand circle bundles with conformal structure, right? And the conformal structure appears in the boundary of the complex hyperbolic space. So imagine that you have this hyperbolic manifold. It's a disk bundle, so the boundary of this disk, there are circles on the absolute of the hyperbolic space. Then you have a circle bundle with conformal structure, because the boundary of the hyperbolic space has conformal structure, right? So there's this conjecture. E is the Euler number, and E is the Euler characteristic. As I said, these two parameters determines the disk bundle uniquely, at least topologically. Okay. So the Gromov person is to open. There is a result by Kontsevich from 1993, where he proves that if it's hyperbolic, then you have an upper bound for the Euler number, right? It's not so simple as this one, but it's more or less one. And the largest Euler number obtained, the relative Euler number, is 0.6. Well, how do I understand this result? Well, I think of this quotient as a comparison between the disk bundle, right, and the tangent space. Because the Euler characteristic is the Euler number of the tangent space. So you can think of this quotient as a comparison between the tangent space and the disk bundle. This inequality also appears, you probably know, from Young or Wood inequality when you are studying flat-oriented circle bundles, right? So, but the problem is that here we don't have flat structure. So this is inequality is not necessarily true, right? This is the real case. But I want to consider not the real case, but the complex one. So the complex one, essentially I will have that M is a complex manifold, and I want to know when this complex manifold, which is four-dimensional, is uniformized by the ball in C2, the holomorphic 2 ball, right? So it's a uniformization problem, right? Okay. So what's the complex hyperbolic space? In essence, the complex hyperbolic space is a ball in Cn, right? So you have ball in Cn, right? And we want to consider a geometry on it. So the way we do it is by approaching it on the projected space. So you consider vector emission form with signature minus, plus, 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 etc. And you define these sets. We have the complex hyperbolic. Is there a lot? Yeah. We have this the complex hyperbolic plane, the boundary, the absolute, and the elsewhere, which is everything else. Okay. So why is this a ball? Because well, we have a map from the ball to the complex hyperbolic plane. The boundary, as Mohammed was saying, has a contact structure. Unlike the real hyperbolic space, the complex hyperbolic space has a contact structure on the boundary, which is called the CR structure, Cauchy-Riemann structure. And the special thing about this is that you have this distribution of planes, and these planes are closed under multiplication by I. They are complex. Okay? So, more than that, we have that all these balls are Caehler. You can consider a Caehler structure like Fubini-Stulch metric. It's similar. And you have this result by Picard, where the group of biholomorphism of the ball is equal to Q(n)(1). Okay? It's a Lie group. So H1c is the Poincare disk, H2c is the complex hyperbolic plane. The complex hyperbolic plane is very different from the four-dimensional real hyperbolic space. Okay? They are different objects. It does not have constant curvature. It's like when you study Fubini geometry, the Fubini of CP2 has no constant curvature, right? Okay. Let me talk about a bit of the zoology in the ball. ball inside C2, right? There are three types of totally geodesic submanifolds. There are geodesics, right? There are complex geodesics, which are essentially the intersection of projected lines with the ball. And there is a third type, which is called real plate, right? These two types, they are hyperbolic space, two-dimensional hyperbolic space. But these ones are Lagrangians, and these ones are complex. They are Riemann surface, okay? And their curvature are different, okay? And it's interesting that the hyperbolic space appear in two different ways, and they are very different between them. And the important thing is that there is no three-dimensional totally geodesic submanifold, and that is a problem because when we want to construct manifolds, you usually use tessellation. And when the boundary is totally geodesic, you can use convexity arguments, right? You can use convexity to verify that the sides are not intersecting each other and so on. Right? So this is anatomy of totally geodesic manifolds. But what I want to explain is how to construct examples. Right? Because these examples, they produce complex hyperbolic manifolds and also contact circle bundles, right? That you can think of as VIHREN manifolds, three-dimensional manifolds fibered by circles. So what kind of three manifolds we use is the following. It's called bisector. A bisector is a very simple object. You just consider a geodesic, right? And for each point, you consider a perpendicular complex geodesic. A complex geodesic, as I said, is a projective line that intersects the complex hyperbolic space. And when you do that for all points, you obtain a cylinder, right? These cylinders are called bisectors. And the beautiful thing is that if you have two complex geodesic and they don't intersect each other and their distance is positive, which is called ultraparallel, then you can consider a minimal distance geodesic and then you can link them by disk. So two ultraparallel complex geodesics can be connected by a bisector. So these are some basic things about hyperbolic geometry. Now I will state the result for the complex field. So assume that, well, a complex surface is complex hyperbolic if it's uniformized by the ball. Okay? Conjecture. Ananin, Grossi, and Kontsevich, they found several examples of complex hyperbolic structures on disk bundles. And comparing with the Gromov-Lossen-Thurston conjecture, they conjecture the same, which I believe is wrong, but so far there's no counterexample. Okay? There is also examples from the 90s, now from 2001, I think, by Goldman, Kapolich, and Lee. Well, so we have this conjecture, it's the same, right? But the difference is that unlike the real hyperbolic space, as far as I know, there is another invariant here, which is called Toledo invariant. The Toledo invariant is essentially, you consider a section, right? And you compute the integral of the symplectic form. You obtain a new invariant. And the interesting thing is that for all examples we know, there is this relation. It's experimental. Okay? And I proved last year that under certain conditions, this is actually true for all, under certain conditions, you always obtain one. And if that is true for all examples, then the conjecture is possible. Okay? But we know it's true just for some examples, some classes of constructors. I'll talk later about it. So far we have talked about the perspective of bundles. I want to talk about the perspective of representation. So we have a surface that we can think of a hyperbolic surface, right? And since we are considered circle bundles, we have that the surface is homotopically equivalent to the total space. And if the total space is complex hyperbolic, you have a representation like this. You can think of gamma as a subgroup of Q2i. So you just have to consider discrete faithful representations, right? And if you want to consider complex hyperbolic discrete bundle, module holomorphic bundle isomorphism, then you have character variety. Okay? So the idea is to imitate classical Teichmüller theory, where we have Teichmüller theory embedded in the representation, the character variety of P1, 1. Okay? So that's the idea, the perspective from representation theory, right? And the Toledo invariant is actually an invariant about representations. So in the context of representations, we have, every time we have a representation of a surface group to Q to 1, you can consider it is invariant, given by that integral, where F is a equivariant map, right, from H1C to H2C. Okay? So there's classical result by Toledo, where the Toledo is bounded by the order characteristic, and it's maximal if and only if there is a complex geodesic which is stable, right? It's called Toledo rigidity. There's another result by Kontsevich, Goldman, and Lee, where they prove that the Toledo can be obtained from the first Chern class when you pull back the tangent space. Okay? And for surface, you can essentially separate the components of the character variety using the Toledo invariant. The same happens for surface. Okay? There are unfold versions for these results in one of my works. Okay. Well, I'll just explain what it is, but I suppose that most of you know what it is. Our fold is just, you know, a space locally modeled by ball, consciented by a finite group of isometries. And you can think of our bundle with fiber F as a map locally modeled by a map like this, where the action of gamma on the product is given by this form, right? Very low-tech perspective, right? You can think of bundles like that. You can develop the theory from this viewpoint using, for instance, topological space, if you don't want to, you know.
Is this point of view good enough to deal with maps between orbifolds in general?
For some maps, like for instance, for covering maps, you can think of covering maps just with discrete fibers, for instance. So for most of my use, it's enough. But not general math. General math, you probably need to choose a stack or choose a legal point, things like that.
What's the structure group?
Huh?
What's the structure group?
What do you mean?
Of the bundle. What's the transition maps?
There is no transition map. It's just a. You can think in the same way that when you study ordinary bundles or manifolds, you can think of maps locally modeled by ball, quotiented ball times F. You can do the same for orbifolds, where you have a diffeomorphism here, locally modeled like this, locally modeled like this, but diffeomorphism. If you don't want to use chart, you can use some general abstract kind of space. In this case, when I develop these kind of things, I use topological space, but you can use any kind of thing you want. Okay? So you don't need charts for that. So orbit bundles, and well, the problem is that when you construct complex hyperbolic disk bundles in practice, you don't work with surface, you work with orbifolds. The reason is because orbifolds are simpler to work with, since they have fundamental groups with less generators. The problem with surface is that the fundamental groups has too many generators, and it's hard to construct fundamental domains. So it's easier to work with orbifolds. So what is my perspective on the Euler number is an adaptation of the Kontsevich view. It's a perspective that you can find, for instance, in books about Seifert manifolds. Right? So the idea is that you consider oriented disk bundle over two orbifold, right? And think of this disk bundle, you can construct circle bundles associated. There's some technicality here, but consider circle bundles associated. Okay, so you have a oriented circle bundle over a orbifold. How do you compute the Euler number? It's similar to the Kontsevich theorem. You have the singular points, and you take a regular point. Okay, and then you remove disks from the surface. When you remove disks from the surface, you obtain an ordinary circle bundle over a surface with boundary. Okay, and a circle bundle like that is always trivial, right? I can explain why later, but circle bundles of punctured surface are always trivial, oriented ones, right? And therefore there is a section, right? So there is a section for that bundle, and you can compare the boundary of that section, because that boundary is on a surface with boundary. There's a drawing on the next slide. It will become clear. Okay, you can compare it with a regular fiber. A regular fiber is a fiber. So we have the surface. You take a point which is not singular. You take a regular point, and above it you have an oriented fiber. Let's call it S. The idea is that you compare the boundary of the section with a regular fiber, and you obtain a rational number. This rational number is the Euler number. So I think it's clear if I give you a drawing. So imagine that you have an orbifold like that. This is the fundamental domain. And then you remove disks around the singular points and around one's regular point. So imagine that you have a circle bundle of it, and you consider a section, right? And you take the boundary of this section. Imagine that the section is a suborbifold. It's embedded on the circle bundle, right? And the idea is that these loops, they are related to the regular fiber. When you compare them, you obtain the Euler number. It's very Kontsevich-like. Very simple. It's very combinatorial. So we have all the things, all the invariants. So we have Toledo invariant, we have Euler number, and now I will discuss what is known, what the examples known. The first examples known, I think, are from Goldman, Kapovich, from 2001. Then Ananin, Gross, and Guzevsky, they constructed some rigid examples with positive relative Euler number, right? What do I mean by rigid? I forgot to mention that. So remember that you have the character variety, right? Rigid means that the character variety is the space of complex disk disk bundles up to holomorphic isomorphism. Okay. So what do I mean by rigid? It means that you cannot deform the complex structure. Like for instance, when you study human surface, the complex structure of the sphere cannot deform, right? And it's non-rigid if you can deform it. Okay. So the examples by Ananin, Gross, and Guzevsky, they were rigid. So, and the Euler number, relative Euler number, was positive. Later on, Ananin and Guzevsky, they constructed examples with Euler number equal to 0. That means that you can construct surface with trivial bundles, right? Trivial disk bundles with complex hyperbolic structure, and that was a Ludmil problem back then. It related to CR structure, to the context structure. Later on, we construct non-rigid examples. They were the first non-rigid examples, as far as I know, right? With negative relative Euler number, a bunch of them, including trivial bundles and the cotangent bundle. Okay? And recently, we constructed some trivial bundles that have a very nice Tech-Miller space. You can, deform them in a very similar way to twists. When you're studying Tech-Miller theory, you have these twists that you use to move on the Tech-Miller space. Here we have something similar on these examples. Okay. So let me explain how these examples are formed. So the simplest type of orbifold, one of the simplest, I think, is this one. So you have this quadrilateral on the hyperbolic plane, on the Kontsevich disk, and you consider a polygon such that you have these angles, right? Where I'm assuming that this number is negative, right? Every time you have a polygon like that, you can consider the group of rotations, G1 and G3, and they will generate a tessellation. Since they will generate a tessellation, you can do the sides and you will obtain a hyperbolic orthofold. So this orthofold has 3 conic points, horns, and it has 3 generators. They are our rotations, and they satisfy this relation. Okay. So this group is function. We have that orthofold, which is hyperbolic. This is not atom, okay? Yeah. So, as I said, we can think of complex hyperbolic disc bundles as elements of the character variety, right? So how do we construct examples? We construct representations and pray that they lead us to complex hyperbolic disc bundles. So the idea, we consider representations like that. We consider these isometries, Rho K, right? Since they have finite order, they are elliptic. Elliptic here means the same as in ordinary hyperbolic geometry. Elliptic means that there is a fixed point inside the hyperbolic space. So they are elliptic, they have a fixed point. Fixed point in the hyperbolic space. And there are 3 situations. If the isometry, you can take the isometry and look at it at SU21. If the 3 eigenvalues are distinct, pairwise distinct, you have this drawing. This drawing is essentially the following. You have 2 stable complex geodesic. They are orthogonal, and they cross at that point. And they are the only stable complex geodesics. Right, so we have this cross. This is the situation where you have the two positive eigenvectors with the same eigenvalue. And this is the situation where you have a positive and a negative eigenvector with the same eigenvalue. Okay? This is a rotation about a point, right? For any complex geodesic you take passing through that point, you have a rotation, keeping that complex geodesic stable. And the other one is a rotation about a complex geodesic. But I will just consider this one. On the paper, we consider the 3 types, but we consider just this one. So we have the isometries. So remember that we have 3 generators. G3. This satisfies some relations. Okay, and remember that their fundamental domain of the base is a polygon like this. What we do, we just imitate the construction. We construct the same fundamental domain, but in higher dimension. How do we do that? We take C3, C1, and C2. C1 is a stable complex geodesic by I1. C2 is a stable complex geodesic by I2, and C3 is a stable complex geodesic by I3. And then we construct C4 as, for instance, I3, C2. Then we connect them by sectors, and we have a candidate for fundamental domain. Of course, it's not that simple. You have to impose several conditions. For instance, you have to impose that these disks are autoparallel. You have to impose that the sides don't intersect each other. You have to impose conditions for orientation of the quadrangle. So there are several conditions, algebraic conditions. Okay. But this is the candidate. And we can also describe the character variety using this case. So that's the candidate. Yeah. So let's consider the part of the character variety where the three isometries, I1, I2, and I3, are regular, which means that the eigenvalues are all different. And if you take two, there is two of these isometries where the eigenvectors are non-orthogonal. This is a generic condition. Imagine that you are considering a generic case. Under this situation, you can parameterize the character variety, at least part of the character variety, by taking the cross from I1, right? And you have the center of I2, right? With these two parameters, these two distances, you can parameterize all the representations, the generic ones, okay? If you want to consider the representations, then you have to make some suppositions, but you can do it, okay? But we are interested in the non-rigid ones. So we have these two parameters, and they parameterize the character variety. Okay. I'm talking too fast. Okay, is it everything clear? Okay. So, numerical example. So in this example, we have the character variety for S334. So we have a sphere with angles 2 pi over 3, 2 pi over 3, and 2 pi over 4. Right? And this is the character variety, the generic ones, right? And it's two-dimensional. This region is the region where we have tessellation, where that candidate for fundamental domain is indeed a fundamental domain. And if that's the case, we obtain a complex hyperbolic distribution, right? On this region, we don't have that fundamental domain fails, but a priori, we don't know if these representations are non-discrete. But that's indeed the case. There are representations in this region that are non-discrete. Okay? So this region contains representations that are non-discrete, and these regions are complex hyperbolic disbundles. Okay? So the region, complex hyperbolic discrete bundles, the light blue contains non-discrete representation. This example is interesting as well because it's the first example of, as far as I know, of complex hyperbolic cotangent bundle. You can construct from it. Okay. So we obtain a lot of numerical data. As I said, we obtained negative relative value numbers. We obtain trivial bundles. Well, and each one of these examples, they actually form a two-dimensional family of examples. Okay? And we obtain parameterizations of a bunch of character varieties. Okay? So these are examples we constructed that are non-rigid. Okay. Now I just want to point out that, remember that here, I assumed that the representations, that the three isometries are regular. If I don't assume they are regular, for instance, if one of these isometry is a rotation, remember that there are three types, right? If one of those isometries are on one of these two types and the other two are regular, then you obtain rigid representations. You cannot deform the complex hyperbolic structure. And if two of them are of these types, then the three are. And the representation will be C function, meaning that the representation has a stable complex geodesy, right? But the only case where you have non-rigid examples is when the three isometries are regular, the first case. Okay.
So can I ask another question? How do you generate these numbers? So you have some large...
Which numbers?
The previous slide.
Here?
From 853.
How do I generate them?
Computer, yeah, like,
it's in computer, yes. I obtained a bunch of examples on MATLAB and use it in Python. Yeah, it's numerical. Essentially, you have a bunch of matrix. You can parameterize them with those distances that I said, right? And then you verify numerically if the conditions for tessellation, they work, right? In essence, like that. You have to search for parameters that work, right? And numerically, I found these, okay? It's just, you know, it's numerical thing. If you want to see how these computations are done, there is an example made on the paper, itself. Okay. This is another family of examples. Here I discuss trivial bundles. They're constructed more or less in the same fashion. So now I want to consider spheres with 5 points, and these points have a null pi. Okay? Is another very simple ortho. And the reason why this group is very interesting, because if you consider representations of H5 onto PSL2R, right? If you consider representations of this type that sends a generator in an element which is not identical. So you take Ri and send to O Ri different from identical. All these representations are discrete for the hyperbolic plane. Right? It is a very interesting case. And it's still open if in the complex hyperbolic plane, if we consider representations on Q1, if its representations are all discrete or not. Right? So, what is this ortho? You can consider this polygon. These isometries are just rotations about points. And I assume that the sum of inner angles is pi. Okay? Under this condition, we have tessellation, and when I glue the sides, we obtain that ortho. Right? Once again, we are using orthofolds because the generators are very simple. Right? We have just 5 generators, and they're all involutions. If we were interested in construct, for instance, disk bundles over the generic surface, imagine, for instance, the genus 2 surface. You need at least, I don't know, 6 generators, right? So, and these generators are not involution, right? Okay. So, consider a presentation, I have these isometries. I will study the case where whole R1 is a reflection on a complex geodesic, and the other one are reflections on points. So, in the complex hyperbolic plane, there are 2 types of involution. There is an involution that has only a point fixed, which is a rotation above that point. It's a reflection, right? And there is the second type, which is a reflection with respect to a complex geodesic. There's 2 types of involutions. So we consider representations of these types, right? I have obtained examples where all 5 are reflections on points as well, but I won't discuss that. So we have these examples. R1 is reflection on geodesics, and the other ones are reflection on points. So generic representations form a 4-dimensional region on the character variety. Okay? You have.
What exactly do you mean by generic?
Generic here means that these points are pairwise distinct, and the points where the reflections happen is not contained on the complex geodesic stable by that one. So think it's there is no accident where 2 points coincide, or the complex plane fixed by one isometry contain the others. Generic geodesics. And the interesting thing is the following: when you study tessellations in the hyperbolic plane, let's say, for instance, we consider polygon. This polygon, 5 sides, hyperbolic plane. and you consider these points. We have 5 points here. And you assume that the sum of the inner angles is 2 pi. And you have reflections are 5. There is something very interesting to do here, which is the following. You can take the geodesic, passing through 2 neighboring points, and you can move them to here, for instance, keeping the distance. Okay. Now you have a new polygon. I don't know if I'm able to draw it. Here. Okay, you can see it. So I just took these 2 points and moved them. Okay? It's a deformation of the polygon. Now I have another representation. We call these bendings. And the thing is, if the sum of inner angles was 2 pi, after deformation, the sum of the inner angles is still 2 pi. So it does not change. So the first representation was discrete, the second one is discrete as well. So this is a way of walking on the Taylor space, just deforming pair of points. And the thing is that you can take 2 representations, modulo isometry, and you can take 2 representations, discrete representations, and connect them by a finite number of bendings in the complex hyperbolic, in the concurrency. Okay? So if you have representations, 2 representations, you can connect them with finite bendings. Okay? This is a result by Bento Gonçalves and Sasha Mann. Okay. So in the complex hyperbolic space, you can do the same. So the idea is that you have some sort of polygon with bisectors, and you can move the sides in a very predictable way, in a similar fashion to here, right? And you can connect 2 representations by these movements, and these movements are called bendings. Okay?
So the character variety is connected?
Is bending connected? No, it's not bending connected. Each one of the components are bending connected.
Each one of the components.
And in this case, there are 2 components. Right? I can describe them if you want.
No, it's
okay. You just have to consider you have the product, just to point out. Imagine that you have R5, R1 equals to 1 in PU to 1, right? Now we want to see this in SU. When you go to SU, this can be 3 possibilities. It can be 1 exponential of 2 pi I over 3, or exponential of 2 pi I over 3. The first case is impossible, and the 2 other ones are not empty. So there are 2 components. These are 2 components. So we have this result. And as I said, we are considering representations where 4 isometries are reflection on points, and the third one is a reflection on the complex geodesic. So with that information, we have a decimation under the certain conditions. And the Euler number is 0. Okay? Is it clear? Okay. So the idea is always to imitate the fundamental domain in the case of surface in higher dimension. Okay, and as I said, in the same fashion that we have here, where we can bend the sides, we can do the same here. Okay? Okay. So far I have explained how we obtain lots of examples. These are non-rigid examples. They are the first non-rigid examples known. And why are they interesting? Why are non-rigid examples interesting? So let me explain one last piece of information. So we have a lot of examples. We want to understand what is going on. So imagine that you have a complex hyperbolic disk bundle or disk orbital bundle. So we have a complex hyperbolic disk orbital bundle, complex hyperbolic, and assume that you have a section which is holomorphic. So we have a section holomorphic. What do I mean by that? You can think of a section as a submanifold. I'm assuming that the section as a submanifold is a Riemann circle. It's holomorphic. In that case, you have this sequence, exact sequence of complex bundles, and you can compare the shared numbers. And from the shared numbers, you obtain this identity, where the tau is the Euler invariant, the E is the Euler characteristic, and the key is the Euler number Euler characteristic. And the tau is negative in this context because, well, it's a choice of symplectic form. If you change the symplectic form, it's positive. Okay. So we have this identity in this case. And the funny thing is that, so we have this basic fact that I just explained. If you have a holomorphic or anti-holomorphic section, then this identity holds. Okay? This is very simple to prove. There is the converse. So when you have rigid representations, there is a simple result by Kontsevich, where he proved that if you have a rigid representation, there is a holomorphic or anti-holomorphic section. So the converse holds for rigid sections, rigid representation. So the question is if it holds for non-rigid. So I proved last year that for all examples constructed using techniques of quadrangles of bisectors, this identity holds as well. Right? And I proved that in a general case, if you have a section where no one of the tangent spaces are complex, then the identity holds as well. So the natural question is the identity always true? Right? It's a natural question. Okay? So what do I expect of you? As I said in the beginning, there is an invariant called the Toledo number, right? And remember that the Toledo number satisfies this. And when the equality holds, there is a complex geodesic which is stable under the action of the representation. I suppose that here we have a similar thing. We have that identity as some sort of rigidity that tells us that there is a holomorphic section. I don't know if that's true, but I think that might be. A second question I would like to ask is if this identity holds. Because there's this formula from symplectic topology, symplectic geometry, called adjunction inequality, but as far as I know, just work for closed manifold, which is not the case. Right? So we have this adjunction inequality. Does it hold in the context of complex hyperbolic space? I don't know. Right? But if it holds, it's related to the above experimental results. And the third one is, if this relation satisfies, does exist holomorphic or anti-holomorphic section? Okay? And that's it, folks.
Are there any comments or questions?
Yeah, I'd like to ask the symplectic people, like Mohammed, what do you think about this? Because this is true in symplectic geometry, right? There are inequalities like that.
Is Miller inequality or something like that?
It's adjunction.
Adjunction inequality, yeah, used to prove Miller conjecture usually.
But usually there are some hypotheses about the manifold has to be closed and there is symplectic area and things like that.
I think the main thing is usually, so there are versions of it in the non-closed case, but almost always there's.
I saw there was one, but they assume that the manifold is tiny. I think it's for Caehler manifolds.
So then what I would say is that the usual assumption is that there's some holomorphicity floating around. So okay, maybe we can talk a little bit later. We can try to identify.
Okay.
Any other comments or questions? So let's thank the speaker again. 4 minutes to restroom and take a breath.
Secret.
Teve alguma outra construção de exemplo como maior?
Não. Esse é o maior.
É o 3 quintos.
É o Kontsevich.
Caramba, não teve nenhuma melhor.
Isso pra caramba.
Eu lembro, o Sasha me obrigou.
Yes.
Eu adoro esse
Mentira. Você não vai ver isso não. Tá bom, tipo, e aí perdi uma vez.
Mas eu acho muito legal. Eu adoro que vocês fazem rolando no centro para formar os Legal. Mas sempre fazer uma pergunta.
Não, a gente vai conversar mais.
Você vai começar a sua deu igual quando eu tive o domingo, vai me ligar. Já falou, a gente vai
muito, cara, sério.
Você não é só situação.
Não tem por que ser.
Foi
Só porque você pegou na coquinha, Não, foi muito legal. Foi muito legal.
Não sei se ficou
O seu sotaque de Carlos Gross e muito, o real está muito da palestra.
Mas é engraçado que, tipo, eu sinto um curso experimental apresentando física teórica.
He was just here writing on the board. He left and went on the board.
I can read
But what about you left? Yeah, he says, man, he left. We're going from museum at Dennis. Right there. Like right after this, there's a Oh yeah, so what can you tell me about the neighborhood?
Okay, guys, maybe we should move on to start, right? Yeah, sure. Other line, of course. So thank you everyone for still attending. It's my great pleasure to introduce to you Semyon Ryshkov from Princeton. That's going to talk about enumerative consequence of cyclotomic symmetry in symplectic homology. Thank you.
Hi, thank you. Thanks for inviting me, and thank you for staying. 7, 6 p.m. I don't know. Very late talk on the second to last day of the conference. I wrote some title, but there's other titles which are valid. There's been some tradition of changing titles, so I'll change it. So this talk really is something about this work is something about oh man. Okay, let's use this other talk.
Take the round ones, these are just
Non-commutative P curvature formula. Okay, and I guess there's some application of some formulae to enumerative results in symplectic topology. So, you know, this conference was supposed to be on the theory of atoms. And so the theory of atoms, whatever it is sort of supposed to be motivated by mirror symmetry. And mirror symmetry is supposed to be about drawing a box like this. So you say there's some x, and there's some x dual, and there's some A side of x, and there's some B side of x dual, and these are supposed to be equivalent. And there's some D side of x model, and some A side of x dual, and these are supposed to be equivalent. And then it's sort of generated by, I mean, all this work is generated by staring at the picture, this x, hoping that something comes out of it. So this whole story about atoms is supposed to be about taking some A side invariance of x and some B side invariance of x and seeing how they interact. Now I'm going to talk about a different area. I'm going to talk about, there's sort of some stuff on here, which I'll kind of describe, and you know what it should be on the A side. And maybe people haven't thought about that for various reasons, but they should. So then, of course, if you have more stuff on here, you can see how it relates to here. Okay, so what's one thing that people say? Well, maybe there's some kind of Gromov-Witten theory of x. That's some A side invariant. And then there's some B side invariant, which is some kind of Hodge theory, or variation of Hodge structures. And again, so atoms are about somehow combining these two, and then you get a better invariant with x. And then under mirror symmetry, the Gromov-Witten theory of x is supposed to match with the Hodge theory of x dual. But the Hodge theory of x dual is some kind of, you know, that's like the characteristic zero part of some motive, okay? And then there's also often some characteristic p part or some p-adic part. And, well, you might ask why, like maybe mirror symmetry is about things over C, but usually, so maybe if this is a symplectic manifold, we're going to focus on the A side. Then the Fukaya category of x, well, this is defined over something like, you know, Q double brackets T, something like that, right? Which is, this is a Snavikov type ring. Sometimes it lifts to something like Z double brackets T. So we saw earlier that there was this kind of all these enumerative variants of this cryptic threefold have some integrality properties. So in that case, you know, on the other side, you should get some x dual, and this is a priori over something like Q double brackets T, because the category of coherent sheaves on this should match with the Fukaya category. But often it has some preferred integral structures. So this happens in examples. You look at the mirror family, and the coefficients of the mirror family are integers. So really over Z double brackets T. Okay? And in this case, okay, now you have a family of varieties over this arithmetically interesting thing. And so you can consider something like the, I don't know, you can look at the crystalline cohomology. Of x dual. And then you get asked, maybe, can you interpret that in terms of invariance of x? Or, you know, some other, you know, Frobenius on x dual mod p, right? That's another thing. That's some kind of nice algebraic geometry object. And you can see if you can see it directly from the symplectic geometry of A. And so I spent a long time thinking about these questions. And this is all motivated by that. Okay, so that's just the kind of context in which whatever I'm going to say sits in this story. Basically, somehow, if you have a variety, there's the kind of characteristic zero part of its motive, and we know a lot about how it's reflected in symplectic topology. But also, it has like characteristic P and p-adic aspects of sort of the motive, and that should also be reflected in symplectic topology in some direct or geometric way. Okay, so here I'll just kind of go and state some result. So let's say x is a quintic threefold. So we think of this as a symplectic manifold. And kind of more generally, there's some larger class for which things will apply. So maybe X is a green lesser. Well, maybe the A side of maybe comes from green lesser mirror pair. Or maybe more generally, the category of X. So X is going to be some compact symplectic manifold. It is defined over Z double brackets T, and this kind of non-degeneracy condition. So this is this sort of condition lets you compare categorical invariance, the category with symplectic invariance of the underlying manifold. So then, we know there's but in all of these cases, so definitely X is going to be C1X is 0. I definitely want the Claude-Yau condition otherwise. So all these categories are Z-graded category. That's important. So you guys, we've been talking about the quantum product. So there's something like, U, Q, G. So there's like grad. So there's this operator you can write down, something like U, T, dt plus quantum multiplication by the symplectic form. Right, this is the small quantum product, so this is some auxiliary degree 2 variable. This is pretty closely related to this, Euler vector field story, but so this, is kind of like T squared d over dt, this sort of operator. So I'm going to call this grad. Okay, and this is this Gaussian connection in the direction of this Navikov variable, and then so the theorem. So this has this is a differential operator, right? And it has integer coefficients. This is a matrix of integer power series. And the reason for that is because quantum multiplication, well, you count 3-pointed Gromov invariance, and there's just this fact that 3-pointed Gromov invariance on a Claude-Yau are always integers. So that's a pretty simple fact that's kind of classical for symplectic topologists, but algebraic geometers sometimes don't learn this.
Well, you're suggesting that there's no algebraic geometric proof of this fact? I
don't know of an algebraic geometric proof, but probably an algebraic geometer should find one. Because m, whatever, GW A03 is always an integer in this setting. And so we can reduce this mod P. So you can reduce grad GM mod P. And now this looks like a connection on a vector bundle characteristic P. And then there's this fact, there's this kind of interesting invariant of a connection in characteristic P. So connection in characteristic P. The P curvature. Okay? So the statement is that if you take grad x, so first I need to tell you one more thing. So given a vector field, x in characteristic P, so this is a derivation on some algebra, you can just iterate the derivation P times, and that's also a derivation. So there's some other vector field x to the P. That's an interesting property of calculus and characteristic P, that if you take the P power of a vector field, that's another vector field. So then you can see to what extent the connection commutes with taking p powers, right? And that's a priori some differential operator, but actually it's a tensor. So actually it's just multiplication by a matrix. It's a tensor. This is called tensorial. And this thing is a name. It's called the p curvature of a connection. Okay. So this is, operation depending on x. So this I would write as the connection with respect in the direction u t dt. Okay. So then you can take grad t dt, so you just divide everything by u, and you can compute its p curvature. And the theorem is that in this setting, this is equal to an enumerative invariant. Okay? So I will explain this enumerative invariant. So what is this? So Q.
There's a little tab at the bottom. Yes.
Nice. Thank you.
So by this setting, you mean for the quintic threefold?
But yes, for example, for the quintic threefold, but in general, the real hypotheses are something like this. So they're hypotheses that are kind of quite annoying to verify, but have been verified in a number of interesting mirror symmetry cases. This is not kind of the best proof. I mean, this argument for this is sort of an argument that says, well, you prove some formula in non-commutative geometry, which basically implies this. And then the reason you can't always apply this is because we don't know that much about Fukaya categories of symplectic manifolds in general. And we don't know non-degeneracy in general. But on the other hand, these are the sorts of things that happen on all these mirror symmetry examples. So,
what is non-degeneracy?
What?
What is that hypothesis? What does it mean?
Non-degeneracy, that's, for example, that's the map from quantum cohomology to Hochschild cohomology hits the unit. Or it's an isomorphism. Yeah, that's the hypothesis. But, yeah. Okay. So what is this? So Q sigma is the following. So you take Q sigma. So you take a class B and a class X. Okay, and B and X are classes in cohomology of X with coefficients in FP. Okay. And so you could make the FP the sort of Nabokov ring version of it. That would be fine. And so what do you do? So this is supposed to be a count like this. So you put some number of copies of B on the side of this sphere. So there are P copies of B. And then you put in one copy of X here, okay? And then you evaluate it, but you kind of keep track of the symmetry. So so the idea is these are some marked points in the equator of the sphere, and the class B is sort of being inserted into those, and you choose the marked points in the equator so kind of evenly, so you have this rotation symmetry of the sphere, and you look at it, inside of it you look at the Z mod P symmetry, and then you sort of count equivariantly with respect to that Z mod P symmetry. Count equivariantly with respect to Z mod P, Z symmetry. Okay? So this is, I'll explain a little more about this, but this invariant has some name. It's called the quantum Steenrod operation. And there's a number of reasons for this. The first one is that, so again, Q sigma dx, if you evaluate at t equals 0, so you look at sort of the classical term, right, the one corresponding to the parts where the spheres are size 0, this is the total Steenrod power of V times x. So if you don't know, if you look at FP cohomology of a variety, then there's some way of taking a class and applying this operation called the Steiner power. And it's like an algebra automorphism, cohomology, and it's sort of this sort of sum of all the possible natural self-transformations from FP cohomology to itself that are stable. And so that's what this operation is if the size of the curve is 0. And the way you can see this is, well, ignore this x and make this curve not be there, and you have kind of a b-fold self-intersection. You have a p-fold self-intersection of the class B. So that would be like b to the p, right? And then you do this equivariantly, so you get lower order terms. And this is the first part of the total Steiner power. The total Steiner power is like a sum of terms, where the first one is b to the p power. Okay. So so the interesting thing here is that people have been thinking about these operations in symplectic topology basically since Fukaya, since the origin of Fukaya categories. They're kind of discussed in the original papers on the idea of a Fukaya category. They satisfy, so I can say lots of things about them, so lots of interesting facts about who's sigma known. And then there's some several instances of this conjecture also known. Okay, but this is the first case when the manifold is Calabi-Yau and has a holomorphic sphere. So this is the first case where x is Cy, and basically these invariants aren't obviously classical and any quantum terms at all. Non-classical. Okay. So the reason for this is because basically these are some kind of mod P invariants, so they're quite hard to compute. Because the way we really compute things like small quantum product is fundamentally through kind of techniques like equivariant localization, and, techniques that use a lot of Q coefficient things. But this is like a very FP coefficient thing. And so it's not obvious how to get your hands on this operation, but this sort of says that it's not really any harder to compute than the small quantum cohomology, which is still pretty difficult, but there's a lot of techniques for computing it at various levels. Okay, so there's a lot more that's worth saying here, but what you might see is that here I have this the small quantum product, this small quantum connection, it's this operation. That's fundamentally about this. So this is about this operation. You take x here, that's kind of the thing you apply it to, and you put in omega here, and then you look at the output. Okay? And so what this says is that if you look at something defined in terms of this operation, and then you take the p-fold cover of this picture along the axis, you get the thing defined in terms of this operation. Okay? So geometrically, there's something else happening, which is that there's this relationship between equivariant invariance with respect to sort of the symmetries of the domain and non-equivariant invariance given by taking p-fold covers. Okay? So, but on the other hand, it's saying that how is that relationship manifested algebraically? It's manifested by this kind of totally alien-looking kind of arithmetic geometry procedure, which is you reduce your connection mod P and you compute this kind of arithmetic geometry invariant. Okay? So I will maybe now say give people credit. So yeah, these are kind of this idea without the spheres was proposed by Betts and Cohen, and then Fukaya kind of suggested that people develop this. But then really the theory of these was sort of first seriously investigated by Nick Wilkins, and he kind of proved a number of interesting things with it, kind of gave the first real computations in the case of the quantum setting. Then Seidel and Wilkins proved some basic properties of it, which is that this thing is covariantly constant with respect to small quantum connection. There's some polymorphic curve picture that proves this. And you can use this to compute it up to low orders, basically. Because you know the classical thing, and you know the small quantum connection, so you go up to some point. And you can't go past that, because you can't solve differential equations in characteristic T. So then, you know, there was some effort to like think about what these mean in some interesting settings. So there's a setting of symplectic resolutions. So for example, T star G mod B, sort of this kind of more 3D mirror symmetry type setting. And there, it was noticed by, you know, there this small quantum connection has this elaborate representation theoretic meaning. And it was noticed that basically the fact that these things are covariantly constant and commute with some extra operators would force it to agree with the P curvature. And this was a sort of an observation of J. Healy. And so he verified, the first time this was noticed was verified by J. Healy in the case of like cotangent bundles to complete flat varieties, using basically a lot of representation theory and this kind of the fact that everything is very rigid. But then later on, you know, people kind of, so there's a paper of Zihong Shen, which kind of tells you what this thing means in terms of Hochschild invariance in the Fukaya category. And then that was used to show that for some large class of faunas, the small quantum connection is an exponential type. So there's this notion of exponential type was defined earlier at this conference. I'm not going to recall it now, but the point is that, you know, arithmetic geometry tells you a lot about how this operation is connected to this connection. And so, you know, if you know that this is also related to some geometric thing that implies more properties of the connection. And then now there's, you know, been some announcement by Seidel and Familiano that they can prove this for all fauna symplectic manifolds. And I basically am talking about the meaning of this formula in non-commutative geometry, which in particular proves it whenever you can compare the Fukaya category with Goemon theory. Okay, so that's sort of the status of things.
Do you have some hope that you could prove this without passing through Fukaya categories?
I am basically extremely confident that it's true unconditionally, and that if you let me hang out, I will give you an unconditional proof. Okay, because somehow the reason this is true is because if you were allowed to make sense of this operation of taking the p-fold cover of this thing and thinking of that as, you know, this curve, then you would prove this geometrically. And I spent a long time understanding what that means in terms of Floer homology. So basically, you know, you should think of this as just something that's true, but the status of this is that, you know, it's not known in general. And also, you know, you could of course choose different. So you could of course look at kind of bulk directions here, and you would expect that. So I haven't proven that, but that's a reasonable conjecture. Okay, so that's the kind of application of some non-commutative P curvature form. Okay, and the point of it is that I'm trying to explain how, if you wanted to capture things like non-commutative Hodge structures, but like non-commutative p-adic Hodge structures and non-commutative mod P Hodge structures, in terms of category theory, what they would mean for Goemon theory. Okay, so that's what this is about. So any questions now? Otherwise, I will continue and actually explain some non-commutative arithmetic geometry.
What's the very strong representation theoretic content of the connection? Because it's a flat. It's just like.
Well, this is a connection in one direction a priori, so of course it's flat. But it's also true that there's other directions, and it's flat in those directions. That's the statement of Frobenius manifolds.
But it's like, is it like a representation of what pi 1?
No, I mean Frobenius manifolds are usually kind of on an affine space. There's not a lot of pi 1, but you can look at monogamy around 0, and that's interesting because this connection has a pole. So the monogamy around 0 is interesting. It's been discussed a number of times throughout the conference. Yeah. This is the thing that people use. They split along this thing to define these atoms. Okay, that's the story. All right. So let me tell you some more arithmetic geometry. So I'm going to tell you what's the formula that you need to generalize to prove this. So there's some classical formula. So let me see how much time I have. 30 minutes? That's not bad. So a formula of Cartier, which I learned from Kaehler and Katzarkov. Although it already is is written in the first paper on the Cartier isomorphism. Okay, I just only recently actually read that paper. It just says things are true. So let me tell you some more things about calculus and characteristic P. So suppose you have F, so K is FP for now. Of course, here K was this kind of Nabokov, you invert T and it's this Nabokov field, but that's not such a big deal. Let's just think about a point, okay? So then also, so A, just for concreteness, you should think of this as like a polynomial ring and some variables. Okay, and maybe you want to invert some of them, because that could be fun. But in general, you should just take like a smooth finite type algebra over FP. Okay. So then you have on one hand polyvector fields on A. Okay, so that's the usual thing, like d over dx times. So this is I. Use your algebra on this, and this acts on differential forms over A. Right, well this is again the usual thing. Okay, and it acts by interior product. Okay, and then also there's the de Rham differential on here. You take the exterior derivative of a differential form. And now I mentioned there was this fact where if you have a vector field, you can send it to its p power. So set of vector fields on A is a restricted Lie algebra. All right. Now, using these operations, you can also form, the Lie derivative. Okay, it's the usual formula for the Lie derivative, just to remind you. But then there's one interesting bit of sort of calculus and characteristic P that one should know, which is the following.
Is there another definition of Lie derivative in this case other than this formula?
Yeah, universal. I mean,
okay.
Yeah, Caehler differentials, universal derivation. I mean, I don't know. These are all characterized by universal properties. Every single thing here.
But there is also some notion of flow in this setting.
You can try to. So if you have a differential equation characteristic P, you can integrate it. But after the P, you divide like order by order, but after t to the p, you're going to divide by 0, divide by p, so that's not allowed. So you can integrate differential equations up to some finite jet, up to the p minus first jet. Yeah. So Cartier isomorphism. So what this says is that the differential forms on A are actually the same as the de Rham cohomology of A. Right, so what I mean by this is you just take cohomology with respect to this operator. And so it's actually realized in a very concrete way. So you take a function, and you send it to its p power. I'm going to just use the Frobenius. And then you take a differential form, something like df, okay, or maybe dxi to be concrete. And you want to send it to d of f to the p, but that would be bad, because this, of course, is p f to the p minus 1 df. But that's 0 in characteristic p, so you divide by p. Okay? And you send it to this, which is really this. Okay?
How can you divide by p?
I just wrote a formula.
Oh.
Okay. And so you should notice that this is a closed form, okay? And this is also a closed, this function is closed, so d of f to the p is 0. I just explained that to you. Right? So this is sending all forms, and then you can extend this by kind of the algebra structure. And this will send any form to a closed form. And then that is called the inverse Cartier isomorphism. And that's what Cartier does. He just says, look at this formula, notice this fact. And then, so you can check on a polynomial algebra that this is actually a bijection onto closed forms mod exact forms. Okay? And so you can write down an inverse. And that is also what Cartier does in his original paper. So what are like, what's a closed, you know, if you have x to the x dx, we just have one variable. When is this closed? Well, it's closed exactly when you have like x to the kp dx over x and x to the kp for some k. Okay, these are the closed one forms. This is the basis of Dirac cohomology. Okay? And so you notice that this formula, what it says is that you send dx over x to dx over x. On the other hand, if you take the vector field x dx, this, its p power is actually x dx again. You should think of this as the Calabi-Yau form on this thing if you invert x. Okay, so it says that this operation preserves the Calabi-Yau form on torus.
So I'm a little confused. Wouldn't every one form be closed? Oh, maybe you took a basis for closed.
So, yeah, so I'm saying take like a larger.
Okay.
Yes, every one form would be. Okay, we can talk about this. Every Dirac cohomology class is represented by one of these. Okay, so this is a basis for Dirac cohomology. So you might see then why it's invertible. I'm trying to indicate that. Okay, so then this formula of Cartier's is the following. It says basically that, or I'm going to write it in this form. It's equivalent to what Cartier wrote, which is that if you conjugate the interior product by a vector field by the Cartier isomorphism, this is some operation on closed forms, and it's actually given explicitly in terms of calculus. So it's the interior product of the p power of the vector field minus the lead derivative, p minus first power of the lead derivative with respect to the vector field times the interior product by the vector field. Okay, so this is this formula. Okay, so the statement is that there's a non-commutative generalization of this formula, and then that implies this. Okay, because it turns out that somehow this formula has some geometric meaning in terms of pictures, and that's how you come up with the non-commutative generalization.
So the left, which side is which?
What? This is a formula in commutative algebra.
Yes.
This is a formula in symplectic topology.
Right.
Somewhere in the middle, there's a formula in non-commutative geometry.
Okay. Yeah. But I'm trying to say, like, is there some analogy where I should think of one side here as corresponding, of this equality is corresponding to one side of that equality, or is it more complicated than that?
You should think of this as either one of these. It's not immediately obvious that this is related to this. Okay. You should think of either one of these. You should basically think of, okay, fine. You should think of this as the p curvature, okay, and this as this, okay? Because this is somehow about taking p-fold covers with respect to the product. And then this is actually extremely closely related to the formula for the p curvature of a differential equation in one variable. Okay, so if you have like an ODE, a linear ODE in one variable, you can compute its p curvature, and it's a very related formula. Okay, so that would be how you would translate this if you wanted to look at it heuristically. Okay. So let me tell you what the non-commutative analog of this formula is. So, and then I'm going to draw a picture, and I'm going to say that somehow this non-commutative analog comes from this picture, and that's why this is true, because this is about the same picture. So non-commutative analogs. Okay, so this is all something that's been discussed. So here in this audience, people know the non-commutative analogs of almost everything. So we know that, if you have sort of differential forms, this is sort of the same thing as functional homology of A, where A is a smooth DGA now. Okay, and then sort of polyvector fields. This is sort of the same as functional cohomology of A, right? And then there's Dirac cohomology. And that's sort of the same thing as cyclic homology. Which I'm going to write like this. Or the underlying chain level object, I'm going to write like this. HH dot A TS1. Okay, because it's to take the structure with respect to the circle action and partial homology. Okay? And so we're kind of getting somewhere. So I said, okay, something about circle action. So the point is, partial homology is some object with a circle action, so he gets this operator delta. And what this object is, in terms of thinking about it in terms of circles, is like you have a chain, you sweep it out by the circle action, you get a chain in one higher degree. And well, there is such an operator on the Hochschild chain complex, it's called the BV operator. I'll write it down explicitly. And then if you take equivariant homology with respect to that circle action, that would be something. And then if you invert the equivariant parameter, you would get this. So that's what this is. And there's all, okay, so we got this guy. Let's get this guy. Well, that's just the Hochschild homology acts on Hochschild homology by cat product. That's the cat product. So that's the interior product. Okay, so we have everything to write down this formula, including this, except for the Cartier isomorphism. But that was given to us by other people. So, what? So, there's some spectral sequence. There's this non-commutative, this Kate spectral sequence. Sometimes it's called the non-commutative Hodge-Durand spectral sequence. Okay? And this is a spectral sequence from something like Hochschild homology of A, double brackets U, to periodic cyclic homology of A. Okay? And then there's a theorem, Clayton. This is a spectral sequence, okay? And then there's kind of another proof of something very closely related, almost the same thing by Phil Matthew. That when A is a smooth, proper over FP, and P is greater, and the Hochschild, I think, cohomology of A is supported, no, the Hochschild homology in this case of A is 0 unless I is in minus PT. This is some kind of dimension, like the prime is large relative to the dimension each. Then the spectral sequence degenerates. Okay, so that's kind of like the Cartier isomorphism. But in fact, there's something, it's very close to an actual map. So the thing that happens is that kind of under a slightly stronger assumption on Hochschild homology, basically you make this range like 1 or 2 bigger. There is an actual isomorphism. HH. You could call this non-commutative inverse Cartier isomorphism. Okay? Okay. So there's the reason for this, I can explain. We can talk about it if you like this. This is a characteristic P. That's important. It's not true in characteristic 0. Badly false in characteristic 0. But you see, you can use this. You can use this to prove that the spectral sequence degenerates in characteristic 0 by spreading out.
But not to produce a split.
Yeah, that's right. You get a splitting in characteristic P. It's exactly analogous to this, but it doesn't survive in characteristic 0. Yeah, that's exactly right.
But Canadian proof goes to reduction.
Yeah, every proof of this basically goes through reduction to characteristic P, except maybe the one where like the actual Hodge theory in characteristic 0 from actual variety degenerates, that goes through analysis. Great. So Okay, so we can write down the analog of this formula. So I only need one more thing. So there's something called the diagonal. So this is a pretty so I need to tell you two more things. The first one is two facts. So first of all, suppose M is a chain complex, is a proper, so like total finite dimensional chain complex over Fp. Okay, well there is this group Cp, which is Z mod Pz, inside S1. And so I said that periodic cyclic homology is like the Tate homology with respect to the S1 action, but actually in this case you have you can also take homology with respect to the Cp action. Cp is inside S1, and this is the same as taking Tate homology with respect to the S1 action and adding on an extra odd variable. Okay, so somehow Cp equivariant homology and S1 equivariant homology are not really different in characteristic P. This is some kind of Bayesian sequence. And then that's fact one. And fact two is that also in characteristic P, there's the following map. So you have a chain complex M. Then you can map it to M tensor over Fp, P times with itself. And then you take Tate homology with respect to the Cp action, where what you're doing here is the Cp action, it rotates these different copies, okay? So you should think of this as like homology of a space. You should think of this as like homology of P copies of a space, and if you give those P copies of a space to actioners produce the copies, then the fixed points are the diagonal, okay? And that's the original space again. And so there's a map of chain, there's a map of chain complexes from here to here, and it just sends x to x tensored with itself P times. And you multiply it by this equivariant variable u to the something, so this is the group preserving. Okay? And then this turns out, after you kind of add on this variable, to be an equivalence. Okay, so there's this is called the diagonal map. So you should just think of it again as a statement that the Cp equivariant, this is some version of localization theorem, but for the group Z mod P, rather than for the group S1. Okay?
For the top bullet, you assume that M is I'm trying to understand, M is a chain complex with a circle action?
No, so here a chain, no, so both of here, here M is a chain complex with some circle action. Okay. Here M is a chain complex with no action. And I give this one, the Cp action, the specific one.
And the circle action is just modeled by having an operator of degree plus whatever minus 1.
Yeah, or maybe like the gap between, so if M has a circle action, then it has a Cp action, that one, this one, and then the gap between these is not.
What is that notation M with a U or
So I just add on this even variable.
Tensor.
Tensor.
Yeah. So this is like the Tate kind of periodicity variable. Okay. So what is this? Just if you guys don't know, so HP is something like 2 periodic Drang homology, really? So that's the same 2 periodicity variable. Okay. All right, so now we can write down the analog of this formula. So the statement is that some diagram commutes. So if you have Hochschild homology of A, you tensor it. So now A is some smooth proper DG algebra over Fp. And then you have Hochschild homology of A. So you can act by the interior product, which is the cat product, to go to Hochschild homology of A. Okay? Then you can act by this C inverse thing to go to Hochschild homology of, and then you add on this variable theta. Doesn't really matter. Hochschild homology. Hochschild homology of A TCP, which is just Hochschild homology of A. So this is just HP of A to S1. Sorry, this variable theta. Or here, so you can act by the diagonal. You tend on this factor with this thing. this non-commutative Cartesian map. And then where this will land you into, so you act on Hochschild cohomology, so you get T copies of Hochschild cohomology. Okay, so this is really the Hochschild chain complex. And you take TCP, and then you tensor this with Hochschild homology. Okay. Okay, and then you do TCP of the whole thing. You do CP equivariant Tate homology. So that's just like the lax monoidal structure of taking cohomology. And then inside here, what you do is, so you can take P copies of the cap product here. So you have P vector fields, and you can just act by each one. And so you can take sort of the P power, you can take that action. And then it turns out that action can be made CP equivariant in a preferred way. And so you take TCP here. Okay? And the statement is that this diagram commutes. So here, this commutes under Hochschild homology assumption, which is, again, it's the same one that goes here. So you can, if you make this range a little bit wider, and then you get this thing. Okay? Now, what's the meaning of making this range a little bit wider? The meaning is actually that there's some object in homotopy theory called the P-complete sphere spectrum. And this is a statement that this algebra lifts to an E1 algebra with a P-complete sphere spectrum. So somehow then you can kind of use methods from stable homotopy theory to prove statements in homological algebra. So I don't know how to prove this kind of directly. I know this is a formula. It's like a simplicial formula that you just verify. But to prove this, I have to use spectrum. Okay, now the point is that this is checked for when A is Fuch X. This thing corresponds, so this cap P TCP is basically the same thing as this quantum Suno operation with respect to, so there's this variable, right? So here you have a class A. Let's say A is an HH2. Okay, so that's like the symplectic form. And then you map it onto the diagonal here. So you kind of do delta A. That's the same thing as the quantum Suno operation with respect to omega. So that was this work of Zihong. Okay? So now this thing, okay, this thing has this connection on it. This Gaussian connection, this sort of non-commutative Gaussian connection. And that's the same as the small quantum connection. And then you can do a little bit more homological algebra, kind of stuff that's known now. The statement is that basically this Gaussian connection comes by, there's some Higgs field acting on this, and then you apply this operator, you kind of do, this thing is really, so when you have a Bernoulli offering, you have to put in a Frobenius pullback. The point is this thing, after Frobenius pullback, the Higgs field becomes a connection, and then under this map, that actually maps the Gaussian connection. That's the theorem of a Petrov-Weintraub-Vygotsky. So, comes from.
This includes some kind of other vector field for this connection?
It's like a scalar thing. Yeah, comes from so plus TEV. So what this implies is that the T curvature of F grad NCGM is equal to this cap T TCP. So if you extend this thing by theta, then it's this operation. Okay, so that's the comparison. Is that the T curvature of the non-commutative Gaussian connection is given by this operation after you just add on this variable theta here. So kind of we'll make it about CP. So this is the sort of actual theorem. And then this implies this, well, this implies the kind of enumerated result by this comparison of Zihong. And the known comparisons between the non-commutative Gaussian connection and the kind of small quantum connection. Okay, so I have 1 minute, I think, so I will draw a picture, because I did not come up with this, okay? I thought of a picture, and then I was like, what does this picture mean in terms of algebra? And so I will draw the picture that like is the meaning of this. Okay?
You do have it formulas.
Formulas, even better. Okay. The geometric meaning is the following. Radical geometric meaning. Okay? So this, as I said, is something about this picture. Okay? And then this is something about this other picture. Okay? So there's a statement that if you look at pictures like this, and you look and you think of the CP action, and you look at the ones which are fixed by the CP action, those come from pictures like this by taking p-fold covers along the central axis. Okay? And so the reason I sort of thought of this formula is actually because I thought of some other formula in symplectic homology, where this picture plus some tools that I define immediately prove that formula. So the point is that if you have so for categories are Claude-Yau, so Hochschild homology and Hochschild cohomology are the same up to a shift, and they're the same as in symplectic homology. So this is like symplectic homology of A. Tensor, this is the product on symplectic homology for an N. Okay? And then there's this map called the cyclotonic structure. And this is a Floer theoretic incarnation of the map which sends a loop to its p-fold cover. And there's somehow some meaning of this operation. Okay, so this sends it to SHM, and then something called a geometric fixed points. Okay, so this is a bit different from this Tate homology construction, but it actually maps to the Tate homology. Okay? And then geometric fixed point, so the fact that this is an equivalence and this is not an equivalence. And so I constructed this map using some kind of equivariant Floer homotopy theory, or something tricky. But it has, again, it has a very naive interpretation, just you send a loop to its p-fold cover. And so here, there's another thing where you can see what comes from this map, and you look at, you see that, and so here you got some map, which is, again, you have like SHM tensor p times tensor SHM, and then you take geometric fixed points of this. And see, so there's this map from p copies and 1 copy to here, and it's to use kind of invariant Floer data. It's an actual CP equivariant map of spectra. And then if you take geometric fixed points of these things, you get exactly these things. So that actually tells you that this diagram commutes. So originally it was like, this is the fact, and then I just figured that probably if it's true in symplectic topology, then it's just always true. So really, there's some, the point is, there's this structure on, well, not on Hochschild homology, but on something called topological Hochschild homology, which is a version of Hochschild homology over the sphere spectrum. And that thing is known now to kind of be very closely related to various aspects of chaotic Hodge theory and sort of the arithmetic aspects of, something about the arithmetic part of the mode of variety. And this thing has a, so topological Hochschild cohomology has an E2 structure. This thing has a cyclotonic structure. And the point is that you should imagine they're compatible. And their compatibility condition is something like this. It's that, whenever you can take a cover of an operatic action, it gives you the fixed points of another operatic action. So you could say that's like the cyclotonic version of the Deligne conjecture. So this theorem is like a consequence of proving, one relation there. Okay. So in general, you don't have to do with FP. There's a version of this for like A is an E1 ring spectrum over any R, where R is an E infinity ring spectrum. you know, if you take R to be ZP, this is now going to be related to the compatibility conditions. This is going to be related to some kind of arithmetic structure of the quantum homology with p-adic coefficients rather than FP coefficients. And you can sort of see what it would be. You can make a conjecture. The statement is that it would be a big Fontaine-Le Fay module, which is the structure you expect on a, you know, it's like a, that's what you, that there's this, that's what like a p-adic non-commutative Hodge structure should be, okay? And, you know, results like this would help you prove something. Okay, so I'm going to stop.
So is there some version which includes lattices or this is the arithmetic that you can
So
gamma conjecture or something?
You could probably try to connect this to the gamma conjecture. I haven't tried. I mean, the gamma conjecture is about the map from like K-theory to Hochschild homology, right? So first there's a map from algebraic K-theory. So the whole point is like, there's this...
Classically it's only the watch.
Yeah, so
yeah.
K-theory, also there's algebraic, so there's algebraic K-theory, and maybe sometimes there's Blanc K-theory, right? And this is with rational coefficients, that's some kind of map. Or there's a different version of this with cyclic homology, and that's the kind of analog of, so this is for topological cyclic homology, which is something like, somehow related to topological Hochschild homology. So you can definitely study the compatibility condition of kind of identities like this with respect to this map. You know, I haven't tried, but it's you know, a reasonable algebra project. Yeah, I don't want to make a conjecture because like I can make a conjecture for, you know, what a p-adic Frobenius manifold should be, but maybe not the p-adic lattices inside of it. I think that's a great question. Okay.
Further questions or comments?
So I think I missed where the Calabi-Yau structure entered into the purely non-commutative.
This has no Calabi-Yau structure. This is a theorem when A is not Calabi-Yau.
Oh.
But Fukaya categories are always Calabi-Yau, which is why you can just put HH equals A, you know. This is actually a source of great confusion for me. Like, there's a dualization. Symplectic topologists do it accidentally all the time. And algebraically, it's like pretty non-trivial. Understanding what the statement should be when you don't have any Calabi-Yau structure was really helpful for figuring out what this theorem in algebra should be that corresponds to this picture. That was like kind of confusing for me.
But could you look at like Fukaya's idle categories or something which doesn't have?
Yeah. This formula, yeah. So yes, yeah.
Further questions or comments?
Is there any chance slip system of differential equations associated to the connection and that X field in this sense? Because you said that you can't do differential equations that much.
I don't know what you mean, I'm sorry. I'm just, there is a Higgs field, but yeah, I mean, you can still write various formulas. You just can't solve the differential equation characteristics.
Okay, so let's thank Simon again.
We will please make your